The Moon hangs in the sky at an average distance of 384,400 kilometers from Earth, a distance so vast that light itself, traveling at nearly 300,000 kilometers per second, requires approximately 1¼ seconds to make the journey. This distance is an average because the Moon's orbit around Earth is an ellipse rather than a perfect circle, meaning the Moon draws closer and pulls farther away in a slow and rhythmic cycle that repeats roughly every month. At its closest point, called perigee, the Moon may approach to within 356,000 kilometers of Earth's surface. At its farthest point, called apogee, it retreats to nearly 406,000 kilometers. The variation between these extremes produces what skywatchers call a supermoon when the full moon occurs near perigee, a time when the Moon appears somewhat larger and brighter in the sky than it does during a more distant full moon. The difference in apparent size between a perigee full moon and an apogee full moon is roughly 14%, a subtle effect that is difficult to perceive without direct comparison, but that contributes to the general sense that some full moons feel more overwhelming in their presence than others. The Moon is the fifth largest natural satellite in the entire solar system, and it is by far the largest moon relative to the size of its parent planet of any rocky world in the solar neighborhood. Its diameter of 3,474 kilometers gives it a surface area of about 38 million square kilometers, comparable to the total land area of all the continents of Africa and the Americas combined. The Moon formed approximately 4.5 billion years ago from the debris ejected when a Mars-sized body collided with the young Earth during the violent early period of the solar system's history. This collision hypothesis, known as the giant impact hypothesis or the Theia impact, is supported by multiple independent lines of evidence, including the close match between the isotopic compositions of rocks from Earth and rocks returned from the Moon by the Apollo missions. The impacting body, which scientists have named Theia, struck the proto-Earth at a grazing angle, and the combined wreckage of both worlds was partially vaporized and partially melted, with the lighter material being flung into orbit around Earth, where it eventually coalesced under its own gravity into the spherical body that became the Moon. The early Moon was dramatically different from the Moon of today. Its surface was covered by a global magma ocean, a churning sea of molten rock, hundreds of kilometers deep, that glowed with fierce heat and would have dominated the sky of the young Earth if any observer had been present to witness it. Over tens of millions of years, this magma ocean slowly cooled from the outside inward, and as it did, lighter minerals crystallized and floated to the surface while denser minerals sank, a process of differentiation that produced the distinct, layered structure the Moon retains to this day. The cooling of the lunar magma ocean was a slow, gradual process that proceeded at different rates in different regions, and its legacy is written into the rocks of the lunar highlands, the pale and heavily cratered ancient terrain that constitutes the earliest surviving crust of any body in the inner solar system. The Moon has no significant atmosphere. What faint trace of gas does cling to its surface is so thin that it barely qualifies as an exosphere, a region where individual molecules are so sparsely distributed that they almost never collide with one another. The total mass of all the gas surrounding the Moon is approximately 10 tons, a quantity that would fit comfortably within a small room on Earth. This near-total absence of atmosphere has profound consequences for the lunar surface environment. Without an atmospheric layer to distribute heat, the lunar surface experiences temperature swings of extraordinary range. In sunlit regions, the temperature of the surface can reach 127 degrees Celsius, hot enough to boil water. In the darkness of a lunar night, the temperature plunges to -173 degrees Celsius. In the permanently shadowed craters near the poles, where sunlight never reaches, temperatures sink even lower, to as cold as -240 degrees Celsius, making these craters among the coldest places in the entire solar system. Without an atmosphere to carry sound, the moon is completely silent. No wind stirs the dust, no rain falls. No weather of any kind occurs on the lunar surface, a stillness so absolute that the boot prints left by the Apollo astronauts in the fine lunar soil will persist unchanged for millions of years, undisturbed by any erosional process apart from the slow, steady rain of micrometeorites that very gradually grinds the surface material into finer and finer dust over geological timescales. The surface of the moon is covered by a layer of broken rock and fine dust known as the regolith, a word derived from Greek meaning blanket rock. This material was created over billions of years by the constant bombardment of the lunar surface by meteorites large and small, which shattered the underlying bedrock and mixed it into a chaotic jumble of fragments, ranging in size from boulders several meters across down to particles smaller than 1/100th of a millimeter. The uppermost layer of the regolith, sometimes called the megaregolith, extends to depths of several kilometers in the most ancient highland regions, while the regolith covering the younger volcanic plains of the lunar Maria is somewhat thinner. The fine component of the regolith, the powdery dust that the Apollo astronauts found coating every surface they touched, has an unusual texture that is quite different from terrestrial dust. Because there is no wind or water on the moon to round and smooth the edges of mineral grains, each particle of lunar dust is irregular and jagged, covered with tiny, sharp protrusions that make the dust highly abrasive and prone to clinging to surfaces through electrostatic forces. The Apollo astronauts reported that this dust was a persistent nuisance, working its way into equipment seals and coating spacesuit visors, and that it had a distinctive smell, often described as resembling gunpowder when they returned inside their spacecraft after surface excursions. The management of lunar dust is one of the significant engineering challenges that future long-duration missions to the moon will need to address. The dark patches visible on the lunar surface that together form the familiar pattern of the man in the moon are called Maria, a Latin word meaning seas. The name was given to these regions by early astronomers who believed they might actually be bodies of water, an idea that persisted into the modern era before the Apollo missions confirmed that the moon is entirely dry on its surface. These vast dark plains are in fact ancient volcanic lava flows that erupted from the lunar interior between approximately 3.5 billion and 1 billion years ago, flooding the floors of enormous impact basins with dark, iron-rich basaltic rock. The largest of the Maria, the Oceanus Procellarum, or Ocean of Storms, covers an area of about 2.5 million square kilometers on the near side of the moon, a region larger than the Mediterranean Sea. The Maria collectively cover about 17% of the lunar surface, but they are concentrated almost entirely on the near side of the moon that perpetually faces Earth, a striking asymmetry that reflects differences in the thickness of the lunar crust between the near side and the far side, and their effects on how easily volcanism could reach the surface in different regions. The basaltic rocks of the Maria are compositionally distinct from the older anorthosite rocks of the lunar events that shaped the early solar system during the period of intense bombardment that scarred the surfaces of all the inner planets. The highland regions of the moon, the pale and heavily cratered terrain that makes up the majority of the lunar surface and dominates the far side entirely, are composed primarily of anorthosite, a rock type rich in feldspar minerals that formed as the lighter materials in the early lunar magma ocean floated to the surface and crystallized. These ancient rocks are among the oldest in the solar system, with ages dating back to more than 4 billion years ago, and they preserve a record of the brutal early bombardment period that is largely erased from Earth's surface by plate tectonics, erosion, and volcanism. The density of craters in the highlands is so high that virtually every square kilometer of terrain has been struck multiple times, creating a landscape of overlapping impact scars that testifies to the violence of the early solar system in ways that no other accessible geological record can match. The study of the crater density distribution across different regions of the Moon has been used to establish the relative ages of different lunar formations and has contributed importantly to the understanding of the timeline of planetary bombardment in the inner solar system, a timeline that has implications for understanding when conditions on the early Earth became habitable for life. The highland rocks returned by the Apollo missions have been subjected to some of the most intensive geochemical analyses ever performed on any extraterrestrial material, revealing details about the composition of the early lunar crust and the conditions under which it formed that would be impossible to determine from remote observations alone. The Moon rotates on its axis at exactly the same rate that it orbits Earth, a condition called synchronous rotation or tidal locking. This precise matching of rotation and orbital periods means that the same hemisphere of the Moon always faces Earth, and the opposite hemisphere, the far side, is perpetually turned away from us. This is not a coincidence. It is the result of billions of years of tidal interactions between Earth and the Moon. Early in the Moon's history, before tidal locking was established, the Moon rotated more quickly. But the gravitational tidal forces exerted by Earth on the slightly asymmetric distribution of mass within the Moon acted like a brake, gradually slowing the Moon's rotation until the two periods synchronized. Once this state was reached, it became stable, and the Moon has remained tidally locked ever since. The far side of the Moon was a complete mystery to humanity until the Soviet lunar spacecraft became the first human-made object to photograph it in 1959. The images revealed a surface dramatically different from the near side, covered almost entirely by ancient cratered highlands with very few maria. This stark difference between the two hemispheres is one of the most intriguing unresolved puzzles in planetary science. The crust on the far side is significantly thicker than on the near side, which may explain why volcanic magma had greater difficulty reaching the surface on the far side, resulting in the relative absence of maria. The reasons for this crustal thickness asymmetry itself remain a subject of active research and debate among planetary scientists. The gravitational pull of the Moon on Earth's oceans creates the tides, one of the most familiar and most consequential manifestations of the Moon's influence on life on Earth. The Moon's gravity attracts the water in Earth's oceans slightly more strongly on the side of Earth facing the Moon than on the opposite side, creating a bulge of water on the Moon-facing side and a corresponding bulge on the far side due to the relative weakness of lunar gravity there compared to the center of the Earth. As Earth rotates beneath these tidal bulges, any given coastal location experiences the bulges passing over it roughly twice each day, producing the characteristic rhythm of two high tides and two low tides that occurs in most parts of the world. The Sun also exerts a tidal force on Earth's oceans, though it is only about 46% as strong as the Moon's, despite the Sun's vastly greater mass, because tidal forces depend on the difference in gravitational pull across the diameter of Earth, and the Sun's greater distance more than compensates for its greater mass. When the Sun and Moon are aligned, at new moon and full moon, their tidal effects combine to produce the especially strong spring tides. When they are at right angles, at the quarter moon phases, their effects partially cancel, and the result is the weaker neap tides. The tidal interactions between Earth and the Moon are not merely cosmetic forces affecting the ocean's surface. They have profound consequences for the dynamics of the Earth-Moon system itself and have played a central role in shaping the evolution of life on Earth over billions of years. The Moon is slowly moving away from Earth. Every year, the Moon retreats by approximately 3 8/10 centimeters, a rate that has been measured with extraordinary precision using retroreflectors placed on the lunar surface by the Apollo astronauts. These retroreflectors, arrays of small corner-cube prisms that reflect laser light directly back toward its source, allow scientists on Earth to bounce laser pulses off the Moon and measure the round-trip travel time with such precision that changes in the Earth-Moon distance of a few millimeters per year can be detected. The cause of this recession is the transfer of angular momentum from Earth's rotation, and Earth's day was much shorter. Calculations suggest that when the Moon first formed, Earth's day may have been only a few hours long, and the Moon may have been close enough to appear dramatically larger in the sky. In the far future, if Earth and the Moon survive long enough, the Moon's recession will eventually halt when Earth's rotation has slowed to the point that it too is tidally locked to the Moon, with both bodies perpetually facing each other. The Moon has a very weak magnetic field today, far too faint to deflect the solar wind as Earth's magnetic field does, but the lunar rocks tell a surprising story of a stronger magnetic past. Ancient lunar rocks, particularly those from the earliest period of the Moon's history, preserve signatures of magnetization, indicating that they cooled in the presence of a much stronger magnetic field than the Moon possesses today. This ancient field is thought to have been generated by convection in a liquid iron core, similar to the process that generates Earth's magnetic field today. At some point, between 3.5 billion and 1.5 billion years ago, the lunar dynamo appears to have ceased, perhaps as the small lunar core cooled completely or as convection within it became too sluggish to sustain the dynamo process. The absence of a global magnetic field today means that the lunar surface is exposed directly to the charged particles of the solar wind and to cosmic radiation from beyond the solar system. This radiation environment the wind and alters the chemical weathering of the surface material in ways that leave visible traces detectable from orbit. The Moon is the only body beyond Earth that human beings have ever visited in person. 12 people walked on the lunar surface between July 1969 and December 1972, all of them American astronauts participating in the Apollo program. The first humans to set foot on the Moon were Neil Armstrong and Buzz Aldrin, who landed in the Sea of Tranquility on July 20, 1969, while their crewmate Michael Collins orbited above in the command module. Armstrong's first step onto the lunar surface and his words upon taking it were transmitted live to an estimated 600 million people watching on television around the world, making it one of the most widely witnessed moments in human history. The 6 successful Apollo landing missions brought back a total of 382 kilograms of lunar rocks and soil samples, material that has been studied continuously since its return, and that continues to yield new scientific insights as analytical techniques improve. The knowledge gained from the Apollo program transformed the understanding of the Moon, the Earth, the solar system, and the processes that shaped the inner planets during the earliest chapter of solar system history. Beyond the scientific return, the Apollo program demonstrated that humans could travel to another world and return safely, a proof of concept whose implications for the long-term future of humanity as a spacefaring civilization have been recognized by nearly every subsequent generation of scientists, engineers, and space exploration advocates in the more than 50 years since the first lunar landing. The surface of the Moon is divided into distinct geological units, that record different episodes in the Moon's 4.5 billion year history, and the study of these units and their relationships to one another is a discipline called lunar stratigraphy. The oldest unit is the pre-Nectarian system, which encompasses all of the lunar crust that formed before the creation of the Nectaris impact basin approximately 4.5 billion years ago. The rocks of this system are found primarily in the ancient highlands and are so thoroughly mixed and pulverized by subsequent impacts that individual rock types are difficult to distinguish. The Nectarian system spans the period from the formation of the Nectaris basin to the formation of the Imbrium basin, approximately 3.9 billion years ago. The Imbrian system, which follows, is divided into an early period dominated by the effects of the Imbrium and Orientale impacts, and a later period during which volcanic eruptions filled the major impact basins with basaltic lava. The Eratosthenian and Copernican systems represent the most recent geological periods on the Moon, characterized by increasingly sparse crater production and the formation of the youngest and most pristine craters that dominate the lunar landscape visible today. The Copernican period is named for the crater Copernicus, a large impact structure about 93 kilometers in diameter, whose bright rays of ejected material, extending hundreds of kilometers across the surrounding Mare surface, indicate it was formed relatively recently in geological terms, perhaps less than a billion years ago. Water ice exists on the Moon, locked in the permanently shadowed craters near the lunar poles, where sunlight never penetrates, and where temperatures are cold enough that ice deposited over billions of years by comets and asteroids has survived without sublimating into space. The existence of this polar ice was suspected for decades before it was confirmed by a series of orbital missions and by the deliberate impact of the L.C. Ross spacecraft into a shadowed crater near the lunar South Pole in 2009. The L.C. Ross impact kicked up a plume of material from the crater floor that was analyzed by a following spacecraft, revealing the presence of water ice along with other volatile compounds including sulfur dioxide, carbon monoxide, and various organic molecules. Subsequent analysis by the Lunar Reconnaissance Orbiter and other missions has mapped the distribution of polar ice in considerable detail, revealing that it is concentrated in patches at the floors and walls of permanently shadowed craters, with the South Pole region appearing to contain substantially more ice than the North Pole region. The discovery of lunar polar ice has significant implications for future human exploration and potential settlement of the Moon. Water is heavy and expensive to transport from Earth, and its availability on the Moon, in at least modest quantities, means that future missions could potentially extract it from the regolith and use it not only for drinking and sanitation, but also for splitting into hydrogen and oxygen for rocket propellant. The ice deposits are not uniform or easily accessible, however, and extracting significant quantities of water from the regolith in the extremely cold and permanently shadowed environment of the polar craters would present considerable engineering challenges. The Moon has been the subject of human observation, mythology, and cultural significance for as long as recorded history extends, and almost certainly for much longer. In nearly every ancient culture that has left written or artistic records, the Moon features prominently as an object of reverence, of timekeeping, of navigation, and of symbolic meaning. The regular cycle of the Moon's phases, from new moon through waxing crescent to first quarter, to waxing gibbous, to full moon, and back again through the waning phases to the next new moon, provided ancient peoples with one of their most reliable and universally accessible calendrical cycles. The period of this cycle, approximately 29.5 days, is the basis of the month, a unit of time embedded in the calendrical systems of civilizations across every inhabited continent. Ancient farmers used the lunar calendar to time their planting and harvesting. Ancient navigators used the position of the moon among the stars to determine their location at sea. Ancient astronomers tracked the moon's motions with increasing precision, gradually discovering the complexities of its orbit that allowed them to predict eclipses and to refine their models of the solar system. The moon's influence on the development of mathematics and astronomy is difficult to overstate. The challenge of predicting lunar motions accurately enough to forecast eclipses was one of the driving problems of ancient astronomy and led directly to the development of sophisticated mathematical techniques in ancient Babylon, ancient Greece, and ancient China that formed the foundations of the mathematical sciences as they developed over subsequent millennia. The moon experiences earthquakes, though scientists call them moonquakes to distinguish them from the seismic events on Earth. The Apollo missions left seismometers on the lunar surface that recorded moonquakes for years, revealing that the moon is seismically active in ways that are similar to, but also distinctively different from Earth. There are several distinct types of moonquakes. Deep moonquakes occur at depths of 700 to 1100 kilometers within the lunar interior and are thought to be triggered by tidal stresses as the moon's distance from Earth varies along its elliptical orbit. Shallow moonquakes occur at depths of only a few tens of kilometers and tend to be stronger than deep moonquakes, sometimes reaching magnitude 5 on the scale used to compare earthquake and moonquake intensities. Thermal moonquakes occur near the lunar surface in the hours around sunrise and sunset, when the rapid temperature changes cause the surface materials to expand and contract and produce cracking sounds detectable by sensitive seismometers. Meteorite impacts also generate seismic signals that the Apollo seismometers detected. One of the most striking findings from the Apollo seismic data was that the moon's seismic signals last much longer than comparable earthquakes on Earth, ringing for up to an hour after a major event, rather than dying away in minutes as terrestrial earthquakes do. This prolonged ringing is thought to be caused by the highly fractured and heterogeneous. The moon's interior has been studied through a combination of seismic data from the Apollo missions, analysis of the lunar samples returned by those missions, and measurements of the moon's gravity field and rotation made by orbiting spacecraft. The picture that has emerged is of a layered body with a small iron-rich core surrounded by a mantle and a crust. The lunar core has a radius of approximately 350 kilometers, much smaller in proportion to the moon's overall size than Earth's core is to Earth's total size, and it consists of an outer liquid layer and a possibly solid inner portion. Surrounding the core is the lunar mantle, a thick shell of silicate rock that makes up the majority of the moon's volume. The mantle is generally solid, but retains some plasticity at depth, and it is from partial melting zones within the mantle that the volcanic eruptions that created the lunar Maria were fed billions of years ago. The outermost layer is the crust, which varies considerably in thickness from place to place. On the near side of the moon, the crust averages about 30 kilometers in thickness. On the far side, it averages closer to 80 kilometers. This asymmetry in crustal thickness between the two hemispheres is thought to be one of the primary reasons why the near side has far more volcanic Maria than the far side, since the thinner near side crust allowed rising magma to breach the surface more easily. The total mass of the moon is 7.34 times 10 to the 22nd power kilograms, about 1/81st the mass of Earth, and its average density is 3,346 kilograms per cubic meter, significantly lower than Earth's average density of 5,500 kilograms per cubic meter, reflecting the moon's smaller proportion of dense iron in its core compared to Earth. Eclipses of the sun occur when the moon passes directly between Earth and the sun, blocking some or all of the sun's light from reaching observers on Earth's surface. Total solar eclipses, in which the moon completely covers the solar disk, are among the most spectacular natural phenomena that can be witnessed from Earth's surface, but they are only possible because of a remarkable coincidence of scale and distance. The Sun is about 400 times larger in diameter than the Moon, but it is also about 400 times farther away, which means that both objects appear nearly the same size in Earth's sky. When the geometry is right and the Moon passes centrally in front of the Sun, its disk precisely covers the solar disk, revealing the Sun's ethereal outer atmosphere, the corona, which is ordinarily invisible against the overwhelming brightness of the solar surface. This coincidence of apparent sizes is purely accidental from the perspective of physics, with no physical law requiring it. It happens to be the case at this particular moment in Earth's history, but it was not always so and will not remain so indefinitely. Because the Moon is slowly moving away from Earth, it is also very gradually appearing smaller in the sky. Millions of years from now, the Moon will appear slightly too small to completely cover the Sun, even at its closest approach, and total solar eclipses will no longer be possible from Earth's surface. In the other direction, billions of years ago, when the Moon was much closer to Earth, it would have appeared much larger in the sky than the Sun, and would have cast a proportionally larger shadow on Earth's surface during solar eclipses. Lunar eclipses occur when Earth passes between the Sun and the Moon, casting its shadow on the Moon's surface. Unlike solar eclipses, which can only be seen from the narrow path traced by the Moon's shadow on Earth's surface, lunar eclipses are visible from the entire night side of Earth simultaneously, making them far more frequently observable by any given person over a lifetime. During a total lunar eclipse, when the Moon passes entirely within Earth's darkest inner shadow called the umbra, the Moon takes on a reddish or orange color rather than disappearing entirely from view. This color arises because Earth's atmosphere bends and filters sunlight around the edges of Earth, and the light that reaches the Moon has passed through the longest possible path through Earth's atmosphere, scattering away the shorter blue wavelengths and transmitting the longer red wavelengths. The exact shade of red that the Moon displays during a total lunar eclipse depends on the current state of Earth's atmosphere, particularly the amount of volcanic ash and other particulates present at high altitudes. After major volcanic eruptions that inject large quantities of material into the stratosphere, lunar eclipses can be strikingly dark and can cause the Moon to nearly vanish during totality. At other times, the Moon may display a brilliant copper-orange color that many observers find hauntingly beautiful. The ancients paid close attention to the colors displayed during lunar eclipses for precisely this reason. Recognizing that they conveyed information about conditions in Earth's upper atmosphere, even without understanding the physical mechanism responsible for the phenomenon. The lunar surface is marked by thousands of craters ranging in size from the microscopic pits left by individual dust-sized micrometeorites to the vast multi-ring basins, hundreds of kilometers in diameter, that are among the most ancient and most prominent features of the lunar landscape. The largest impact basin on the Moon is the South Pole Aitken Basin, a depression about 2,500 kilometers in diameter and 13 kilometers deep, located on the far side of the Moon. This enormous structure is one of the largest and oldest impact craters in the solar system, formed by a collision so powerful that it excavated material from the Moon's mantle and spread it across a huge region of the far side surface. The Imbrium Basin on the near side, about 1,100 kilometers in diameter, is another of the Moon's great impact scars, and the lava-flooded floor of this basin forms the dark, circular plain that constitutes the most recognizable feature of the man in the Moon, as seen from Earth. Individual named craters on the Moon number in the tens of thousands. They range from perfectly circular bowls a few kilometers across to complex structures with central peaks, terraced walls, and elaborate surrounding ejecta patterns that record the dynamics of the impact process in intricate detail. The study of crater morphology and its variations with crater size has provided fundamental insights into the mechanics of impact cratering that apply throughout the solar system, making the lunar surface a kind of natural laboratory for understanding the physics of planetary bombardment. The Moon has been observed through telescopes since Galileo first turned a telescope toward it in 1609, sketching its mountains, craters, and dark plains in drawings that established forever the principle that the Moon was a world with its own complex geography rather than a perfect celestial sphere, as many earlier thinkers had supposed. Galileo estimated the heights of lunar mountains from the lengths of the shadows they cast at certain angles of illumination, demonstrating that the lunar terrain was as rugged as the mountains of Earth. Subsequent generations of astronomers mapped the Moon's surface in increasing detail: the Sea of Fertility, the Bay of Rainbows. These names, accumulated over 4 centuries of telescopic observation, form a rich cultural layer of human meaning deposited onto a landscape of ancient stone, a record of the process by which each generation of observers brought their own intellectual traditions to bear in trying to understand and categorize the Moon's complex surface. The naming conventions established in the 17th century by Giovanni Battista Riccioli in his Atlas of the Moon remain the foundation of the official nomenclature maintained today by the International Astronomical Union. The composition of the lunar soil, the fine particulate material making up the uppermost layer of the regolith, has been determined in detail through laboratory analysis of the samples returned by the Apollo missions and by robotic sample return missions. The lunar soil contains a mixture of minerals including plagioclase, feldspar, pyroxene, olivine, and ilmenite, along with glass beads created by the heat of micrometeorite impacts, fragments of various rock types, and particles of metallic iron derived from both the lunar rocks themselves and from the meteoritic material that has bombarded the Moon over billions of years. One of the most scientifically interesting components of the lunar soil is the presence of helium-3, a rare isotope of helium that is extremely scarce on Earth, but has been implanted into the surface layers of the lunar regolith over billions of years by the solar wind. Helium-3 is of interest as a potential fuel for future nuclear fusion reactors, and some scientists and engineers have proposed that mining helium-3 from the lunar soil could provide an energy source for both lunar settlements and for export to Earth. The concentrations of helium-3 in the lunar soil are quite low, however, and extracting significant quantities would require processing enormous volumes of regolith, a technical challenge that has not yet been convincingly addressed in terms of economic or energetic feasibility. The lunar soil also contains oxygen locked within mineral structures, and extracting this oxygen by heating and reducing the minerals is considered one of the more promising approaches to in situ resource utilization for future human lunar missions. The phases of the Moon follow a predictable cycle of approximately 29.5 days, known as the synodic month, which represents the time required for the Moon to return to the same angular position relative to the Sun as seen from Earth. This cycle differs from the sidereal month, the period of approximately 27.33 days required for the Moon to complete one full orbit relative to the distant stars, because Earth itself is moving along its orbit around the Sun during that time, and the Moon must travel a little farther than one full orbit to catch up with the Sun's apparent position in Earth's sky. The phases arise simply from the geometry of how the Moon's illuminated half is oriented relative to an observer on Earth. At new moon, the moon is on the same side of Earth as the sun, and its dark side faces Earth, making it invisible against the brightness of the day sky. As the moon moves along its orbit, an increasing sliver of its illuminated side becomes visible from Earth, and the moon progresses through the waxing crescent, first quarter, and waxing gibbous phases. At full moon, the Sunday, the moon influences life on Earth in ways that extend well beyond the obvious effects of tidal forces and the provision of light at night. There is compelling evidence that the moon's existence and its specific mass and orbital properties have played a significant role in stabilizing Earth's axial tilt over geological time, contributing to the climate stability that may have been important for the development of complex life. Earth's axial tilt, currently about 23.5 degrees, is what produces the seasons, and if this tilt varied chaotically over geological time, the climatic consequences would be severe. Computer simulations suggest that without the moon's stabilizing gravitational influence, Earth's axial tilt could vary dramatically over millions of years, potentially swinging from nearly 0 degrees to as much as 85 degrees, a range of variation that would produce extreme climatic instability, incompatible with the long-term persistence of complex ecosystems. The moon's mass is large enough relative to Earth's to provide significant stabilization of this axial wobble, keeping it within a relatively narrow range on timescales relevant to the evolution of complex life. This role of the moon in stabilizing Earth's climate has led some researchers to suggest that large moons around rocky planets in the habitable zones of other stars might be important factors in determining whether those planets can sustain complex life over the billions of years required for intelligence to evolve. The question of how common such large moons are around Earth-like planets in other solar systems is one of the active areas of inquiry in the field of astrobiology. The moon's surface gravity is approximately 1/6 of Earth's surface gravity, a difference that arises from the moon's smaller mass and its smaller radius, which together produce a gravitational field at the surface that accelerates falling objects at only 1/6 meters per second squared, compared to Earth's 9.8 meters per second squared. This reduced gravity has profound implications for movement on the lunar surface, as the Apollo astronauts demonstrated when they found that walking on the moon required adapting to a very different biomechanical environment than anything available in training on Earth. The astronauts found that a kind of loping kangaroo hop was often the most efficient mode of locomotion, and that the low gravity allowed them to carry heavy equipment and life support systems that would have been impossible to transport on Earth's surface. The reduced gravity also affects how materials behave on the moon. Slopes that would be stable on Earth can be unstable on the moon because the lower gravity that holds surface material in place is less effective at preventing mass movements. At the same time, the absence of water and the reduced role of erosion mean that very steep slopes can persist on the moon for billions of years. The combination of low gravity and no atmosphere means that the moon cannot retain gases, and any material ejected from the surface by impacts or volcanic activity at higher than escape velocity, approximately 2.4 kilometers per second, will leave the moon entirely and escape into space. The moon's escape velocity is substantially lower than Earth's 11.2 kilometers per second, which is one reason why the moon lost its early atmosphere while Earth retained and subsequently replenished its own. The brightness of the full moon on a clear night is sufficient to cast visible shadows on Earth's surface, to read text without any other illumination, and to influence the behavior of many animals and plants in ways that ecologists have studied in considerable detail. The full moon provides roughly 1/400,000th as much light as direct sunlight, a ratio that seems negligible until one considers how sensitive biological systems can be to even very small differences in ambient light levels. Coral reefs synchronize their annual mass spawning events with the lunar cycle, with enormous numbers of coral polyps releasing gametes into the ocean simultaneously during the nights following the full moon in late spring or summer. This synchronization is thought to increase the probability of successful fertilization by ensuring that eggs and sperm from different individuals are present in the water at the same time, and the use of the lunar cycle as a timing signal ensures that the event occurs at a predictable and consistent time each year across the entire reef community. Various species of shore-nesting birds adjust their nesting behavior in response to the lunar cycle. Some insect species emerge as adults in synchrony with the lunar cycle. Many marine organisms display lunar periodicity in their reproductive behavior, and the mechanisms by which they detect and respond to the lunar cycle include not only the direct photosensitivity of their eyes and skin, but also responses to the gentle variations in Earth's gravitational field associated with the Lunar Moon's position. The extent to which life on Earth has evolved with the lunar cycle as a fundamental environmental rhythm, as basic in its influence as the daily cycle of light and dark, or the annual cycle of the seasons, is a subject of continuing ecological investigation. The history of human missions to the Moon beyond the Apollo program includes a series of robotic missions that have collectively transformed the scientific understanding of the lunar surface in the decades since the last astronaut walked on the Moon in December 1972. The Soviet Union's lunar program, which ran from 1959 to 1976, achieved a series of important milestones, including the first lunar impact, the first images of the far side, the first soft landing, the first automated sample return, and the deployment of 2 automated rovers called Lunar that traversed tens of kilometers of the lunar surface. The Clementine mission of 1994, a joint project of the U.S. Department of Defense and NASA, produced the first global topographic and spectroscopic maps of the lunar surface and returned early evidence for the presence of water ice in the polar regions. The Lunar Prospector mission of 1998 further mapped the Moon's elemental composition from orbit and strengthened the evidence for polar water ice through its neutron spectrometer observations. In more recent years, the Indian Chandrayaan-1 mission confirmed the widespread presence of hydroxyl and water molecules on the lunar surface through its observations in the infrared. And the Chinese Chang'e program has deployed multiple landers and rovers to the lunar surface, including the Chang'e 4 mission that made the first soft landing on the far side of the Moon in January 2019. The Lunar Reconnaissance Orbiter, operating since 2009, has produced global maps of the Moon at resolutions down to 0.5 meter per pixel, providing a complete and detailed global survey of the lunar surface that will serve as the foundation for planning future human return missions. The Moon plays a role in regulating Earth's calendar through the mechanism of the Metonic cycle, a period of approximately 19 years, after which the Moon returns to almost exactly the same position in the sky relative to the Sun and the stars. This cycle, discovered by the Greek astronomer Meton of Athens in the 5th century BCE, means that lunar phases repeat on the same dates of the solar year approximately every 19 years, a coincidence that arises from the fact that 235 lunar months correspond very closely to 19 solar years. The Metonic cycle was used in antiquity to reconcile lunar and solar calendars, providing a way to keep a lunar calendar approximately synchronized with the seasons over longer periods. It is still used today as the basis for computing the date of Easter in the Christian calendar and for determining the dates of Passover and other Jewish holidays that are defined in terms of the lunar calendar. The moon's influence on the calendar extends throughout virtually every major human civilization. The Islamic calendar is a purely lunar calendar in which each month begins with the sighting of the new crescent moon, and the year contains either 354 or 355 days, shorter than the solar year by about 11 days, so that the months cycle through all the seasons over a period of about 33 years. The Hebrew calendar is a lunisolar calendar that adds an extra month in certain years of a 19-year cycle to keep it aligned with the solar year while maintaining the lunar months. The Chinese traditional calendar is also lunisolar, using a similar system of periodic intercalation to maintain the correspondence between lunar months and the solar cycle that determines the seasons. The surface of the moon preserves evidence of the solar wind in a way that no other accessible planetary surface does, because the absence of a significant magnetic field and the near total lack of atmosphere allows the particles streaming from the sun to strike the lunar surface directly, implanting themselves into the minerals of the uppermost layer of the regolith. The solar wind is a continuous stream of charged particles, primarily protons and electrons, that flows outward from the sun at speeds of 300 to 800 kilometers per second. These particles carry within them a chemical record of the sun's composition at the time they were emitted, and by analyzing the solar wind-implanted gases in lunar soil samples of different ages, scientists can, in principle, reconstruct how the composition and intensity of the solar wind has varied over billions of years. This chemical record, preserved in the lunar regolith as a sort of natural archive of solar history, is one of the unique scientific assets that the moon offers for understanding the long-term evolution of the sun, information that cannot be obtained from any other accessible source. The solar wind also contributes to a process called space weathering, in which the constant bombardment of the lunar surface by solar wind particles and micrometeorites gradually alters the optical properties of the surface material, darkening and reddening it over time. This space weathering process affects all airless bodies in the solar system, including asteroids and the moons of other planets, and the moon's well-studied regolith provides a standard of comparison for understanding space weathering processes elsewhere in the solar system. The moon is the target of renewed human exploration efforts in the 21st century, with space agencies and commercial companies from multiple nations pursuing plans for returning humans to the lunar surface for the first time since 1972. NASA's Artemis program, initiated in the late 20-teens, aims to land the first woman and the next man on the moon at or near the lunar South Pole, where the presence of water ice and the relatively favorable conditions for solar power generation at sites near the crater rims make the region attractive for establishing a sustained human presence. The European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and commercial partners are collaborating with NASA on the Lunar Gateway, a small space station intended to orbit the moon and serve as a staging point for surface missions. China's lunar program is advancing toward crewed landings in the late 2020s and has articulated ambitions for establishing a research station at the lunar South Pole in collaboration with Russia and other partners. India's Chandrayaan-3 mission achieved a successful soft landing near the lunar South Pole in August 2023, making India the fourth country to achieve a soft landing on the moon and the first to land in the South Polar region. The renewed interest in the moon reflects both the advancing capabilities that make lunar return increasingly feasible and the growing recognition that the moon offers unique scientific, strategic, and economic value as the nearest point of comparison for understanding Earth's history, as a potential source of resources for space operations, and as a proving ground for the technologies and operational experience that will eventually be needed for human missions to Mars and beyond. The Moon rotates exactly once on its axis for every orbit it completes around Earth, a state called synchronous rotation that keeps one face perpetually turned toward Earth and one perpetually turned away. The mathematical precision of this alignment is a result of tidal locking, a process that has operated over billions of years. Although the Moon's rotation rate is steady, its orbital speed varies slightly as it follows its elliptical path, moving faster when closer to Earth and slower when farther away. This variation means that the Moon's rotation and its orbital motion do not always exactly match at any given moment, even though they match perfectly over each complete orbit. The result is a gentle rocking motion called libration that, over time, allows observers on Earth to see slightly around each edge of the Moon. Through libration, about 59% of the Moon's total surface area becomes visible from Earth at one point or another, rather than just the 50% that would be visible if there were no libration. There are three types of libration. Libration in longitude arises from the variation in orbital speed, just described. Libration in latitude occurs because the Moon's equatorial plane is slightly tilted relative to its orbital plane, allowing observers to see slightly over the north or south poles alternately as the Moon progresses along its orbit. Parallax libration, also called diurnal libration, is a smaller effect caused by the fact that an observer on Earth's surface shifts position as Earth rotates, gaining slightly different vantage points on the Moon at different times of night. The combined effect of these librations has been studied by astronomers for centuries and was essential for producing complete maps of the lunar surface before spacecraft first circumnavigated the Moon. The geology of the Moon records a history extending back to the formation of the solar system, and the rocks returned by the Apollo missions have provided some of the most precise age determinations available for any material in the solar system. The oldest lunar rocks, samples of ancient Highland anorthosite, have been dated by radioactive decay methods to 4.4 to 4.5 billion years, ages that approach the age of the solar system itself. These ancient highlands rocks formed during the cooling of the lunar magma ocean and represent the earliest surviving crust of the Moon. Younger rocks from the lunar Maria are dated to between approximately 3.8 and 1.2 billion years old, reflecting the prolonged volcanic activity that filled the impact basins with basaltic lava during a long chapter of the Moon's geological Middle Age. Some mere basalts collected by Apollo 17 have been dated to as recently as 2.9 billion years, while orbital spectroscopic observations suggest that some volcanic deposits on the near side may be as young as 1 to 1.5 billion years old. After the cessation of major volcanic activity, the Moon's surface has remained geologically quiescent, with no plate tectonics, no volcanic eruptions, and no significant erosion to resurface the ancient terrain. The geological record frozen into the lunar surface and the rocks returned from it has been used not only to understand the Moon's own history, but also to calibrate the impact flux in the inner solar system over time, providing a timeline for the bombardment history of all the terrestrial planets, including Earth, Venus, and Mars. The surface of the Moon near the poles experiences conditions quite different from those at lower latitudes, owing to the Moon's nearly zero axial tilt relative to its orbital plane. Earth has a substantial axial tilt of 23.5 degrees, which causes the polar regions to experience seasons with large variations in the amount of sunlight received through 1.5 degrees above the horizon as seen from the lunar poles. This perpetually low solar illumination angle creates a landscape of extremes at the poles. At the summits of tall crater rims and central peaks, the sun hovers perpetually near the horizon, providing nearly uninterrupted sunlight for months at a time. These areas of near-permanent illumination are called peaks of eternal light. and they are considered extremely valuable real estate for future lunar outposts because they receive near-continuous solar power and experience relatively moderate temperatures compared to locations that cycle through lunar day. In the deeply shadowed interiors of craters, whose walls are tall enough to block even the grazing polar sunlight, temperatures remain perpetually frigid and solar power is unavailable. But these are precisely the locations where water, ice, and other volatiles have accumulated over billions of years. The juxtaposition of resources available near the lunar poles, with solar power available at the crater rims and water ice available in the crater floors, makes the polar regions the most scientifically interesting and practically valuable locations on the Moon for future human exploration and potential settlement. The Moon has accumulated a remarkable collection of meteorites originating from other bodies in the solar system that have struck its surface over billions of years. Because the Moon has no atmosphere to slow and disintegrate incoming objects and no geological processes to bury or resurface the ancient terrain, it retains a much more complete record of the bombardment history of the inner solar system than any other terrestrial body. Among the meteorites found on the lunar surface by the Apollo missions, or identified in the samples returned to Earth, were fragments of rock with compositions matching those of meteorites known to originate from the asteroid belt, fragments of material that may have originated from comets, and even a few fragments tentatively identified as having originated from Mars or other planets. The Moon itself has contributed meteorites to other bodies. A number of meteorites found on Earth have compositions and ages that match those of lunar rocks, and scientists believe they were blasted off the Moon by major impacts and eventually fell to Earth after spending varying amounts of time traveling through space. These lunar meteorites, of which more than 400 are currently known, have been found primarily in Antarctica and in hot desert regions, where their unusual compositions make them easier to identify among the surrounding terrestrial rocks. They have extended the geographic sampling of the Moon well beyond the 6 Apollo landing sites, providing glimpses of lunar terrain types and geological units that were not sampled by the Apollo missions, and helping to build a more complete picture of the Moon's geological diversity. The Moon has served as a mirror for understanding Earth's own geological history in ways that go beyond simply providing a record of the impact flux in the inner solar system. The giant impact hypothesis for the Moon's formation, which holds that the Moon formed from debris ejected by a Mars-sized body colliding with the young Earth, has profound implications for the early history of Earth itself. The collision that formed the Moon was among the most violent events in Earth's history, releasing enough energy to melt the entire outer portion of Earth to depths of several thousand kilometers and fundamentally resetting the composition and structure of the early Earth. The mixing of terrestrial and impactor material during this event, and the subsequent differentiation and cooling of the deeply molten post-impact Earth, would have determined many of the fundamental characteristics of Earth's composition that persist to this day. The isotopic similarity between Earth and Moon rocks, which was crucial in establishing the giant impact hypothesis as the leading explanation for the Moon's origin, also provided a remarkable constraint on the nature of the impacting body, suggesting that it had to have had a very similar composition to Earth's mantle, rather than the different compositions characteristic of most other bodies in the inner solar system. Understanding the Moon's formation is therefore inseparable from understanding the formation and early evolution of Earth itself, and the study of lunar samples continues to provide new insights into this violent early chapter of our planet's history that would be impossible to obtain from the study of Earth's rocks alone. Since the geological record of Earth's first billion years has been almost entirely erased by subsequent geological activity, the Moon exerts its gravitational influence not only through the tides, but also through a more subtle effect on the length of Earth's day. As the Moon raises tidal bulges in Earth's oceans and in the solid body of Earth itself, and as Earth rotates and carries these bulges forward of the line connecting Earth and Moon, the Moon's gravity pulls backward on these bulges in a way that gradually slows Earth's rotation. Over billions of years, this tidal braking has caused Earth's day to lengthen significantly. In the earliest days of Earth's history, shortly after the moon-forming impact, Earth may have rotated so rapidly that a day lasted only 5 or 6 hours. Geological evidence preserved in the growth patterns of ancient tidal rhythmites, sedimentary layers, whose thicknesses record the strength of tides in ancient shallow seas, and in the growth bands of fossil corals, which preserve records of the number of days in each ancient year, has allowed scientists to reconstruct the length of Earth's day at various points in geological history. The contribution to Earth's thermal budget over geological time is not negligible. The Moon's surface displays a category of geological features called rills, long, narrow troughs, or channels that can extend hundreds of kilometers across the lunar landscape. These features come in two broad types. Sinuous rills are curved, meandering channels that closely resemble river valleys on Earth, though they were formed not by flowing water, but by flowing lava during the period of intense volcanism that created the Lunar Maria. The most famous of these is Hadley Rill, a long, sinuous trench about 1.5 kilometers wide and up to 400 meters deep, visited by the crew of Apollo 15 in 1971. Straight and arcuate rills, by contrast, are formed by tectonic processes, the stretching and cracking of the lunar crust in response to stresses generated by the weight of lava loading in the Maria, or by the cooling and contraction of the lunar interior. These linear features are essentially fault systems, places where the crust has pulled apart and one side has dropped relative to the other, forming long straight valleys bounded by steep walls. The study of lunar rills has provided important information about the volcanic and tectonic history of the Moon and about the mechanical properties of the lunar crust. More recent observations from the Lunar Reconnaissance Orbiter have revealed a category of very young features called lobate scarps, long low ridges formed by compression sunlight from ever reaching the crater floors, have remained in permanent darkness for perhaps 2 to 3 billion years or even longer. During this time, they have served as cold traps, accumulating any water vapor or other volatile molecules that drifted or were delivered to the polar regions and condensed on the frigid surfaces. The temperatures in these regions, measured by orbiting spacecraft, reach as low as -240 degrees Celsius in the most extreme cases, making them the coldest known places in the solar system, colder even than the distant reaches of the outer solar system, where sunlight is far weaker. Within the regolith of these permanently shadowed regions, the water ice and other volatiles are not distributed in thick, easily accessible deposits as one might hope. Instead, they appear to be mixed in at concentrations of perhaps a few % by weight with the surrounding rock and dust, requiring that large volumes of regolith be processed to extract useful quantities of water. The chemical complexity of the material found in permanently shadowed regions is also notable, with volatile species ranging from water ice to carbon dioxide, methane, ammonia, and complex organic molecules, all potentially delivered by the comets and asteroids that have struck the Moon throughout its history and accumulated in these frigid natural cold traps over billions of years. The Moon's association with mythology and cultural practice extends across virtually every human culture that has been documented. In ancient Mesopotamia, the moon god Sin was one of the most important deities in the pantheon, associated with wisdom, magic, and the measurement of time. In ancient Egypt, the moon was associated with the god Thoth, the divine scribe and master of knowledge. In ancient China, the moon is associated with the goddess Chang'e, who, according to legend, flew to the moon after drinking an elixir of immortality, a story that has given its name to China's ongoing series of lunar exploration spacecraft. In ancient Greece, the moon was personified as the goddess Selene, whose name lives on in the study of lunar geology, which is called selenology. The Norse tradition associated the moon with the god Mani, who drove the moon across the sky in a chariot. Indigenous cultures around the world developed their own rich traditions of moon mythology, and the sheer diversity of lunar stories and beliefs across human cultures testifies to the universal fascination that the moon has inspired in every human society that has had the opportunity to observe it. The moon's consistent and reliable cycle of phases made it a universal timekeeping device that transcended cultural boundaries, and its nighttime brightness made it a source of practical utility for travel, agriculture, and navigation that all human societies depended upon. The cultural weight of the moon in human history is so profound that even in the modern age, when scientific understanding has replaced mythological interpretation, the moon retains a powerful grip on the human imagination that draws billions of observers to watch each full moon rise, with an attention that goes well beyond mere curiosity about a physical object in space. The properties of the lunar regolith make it both a challenging and a potentially useful material for future human exploration and habitation of the moon. The abrasive, sticky, glass-laden dust that covers the lunar surface poses engineering challenges for any equipment that must operate in contact with it. But the same material also contains resources that could be exploited for construction and manufacturing purposes on the moon, reducing the need to transport massive quantities of material from Earth at enormous expense. Lunar concrete, made by mixing lunar regolith with small amounts of water extracted from the polar ice deposits, has been studied as a potential construction material that could be used to build radiation-shielded habitats, landing pads, and roads on the lunar surface. The regolith itself can be used as a raw material for three-dimensional printing of structural components, with experimental work having demonstrated that shapes similar to brick can be printed from simulated lunar soil using microwave heating or by mixing it with small amounts of binders. Oxygen constitutes about 45% by weight of the lunar regolith, locked up within the mineral structures of the silicate and oxide minerals that make up the bulk of the soil. Extracting this oxygen by heating the regolith and chemically reducing the oxide minerals would provide a supply of breathable gas and rocket oxidizer that would be invaluable for a lunar base. The combination of these in situ resource utilization possibilities is a major driver of the renewed interest in the moon as a destination for sustained human presence, since the ability to live off the land dramatically changes the economics and logistics of operating a long-duration outpost on another world. The moon has its own very thin and dynamic atmosphere called an exosphere, composed primarily of atoms and molecules released from the lunar surface by solar radiation, micrometeorite impacts, and other processes. The most abundant components of the lunar exosphere include helium, neon, argon, sodium, and potassium, as well as water vapor and other trace species. The total amount of gas in this exosphere is so small that it would represent a near-perfect vacuum by terrestrial standards, with a total mass of only about 10 tons spread over the entire lunar surface. Despite its extraordinary thinness, the lunar exosphere is scientifically interesting because it provides a window into the complex exchange of atoms between the lunar surface and the space environment, recording information about the rates at which different species are released from the surface and lost to space. Sodium and potassium in the lunar exosphere can be observed from Earth using specialized telescopes because they emit light at wavelengths where the sky background is relatively dark, and observations of these species have been used to study how the lunar exosphere varies with solar activity, with the phase of the Moon, and with the impact of specific meteor showers that deliver additional material to the lunar surface. The study of the lunar exosphere is relevant not only for understanding the Moon itself, but also for understanding the exospheres of other airless bodies in the solar system, including Mercury, several of the moons of Jupiter and Saturn, and the larger asteroids, all of which have thin exospheres maintained by similar surface release processes. The Moon's gravity, though only 1/6 of Earth's, is strong enough to have played a major role in shaping the history of the Earth-Moon system and continues to exert measurable effects on Earth today. The gravitational influence of the Moon extends through space in all directions, affecting not only Earth's oceans and crust, but also the behavior of spacecraft operating in the Earth-Moon system and the orbits of other small bodies that occasionally pass through the region. The gravitational potential landscape of the Earth-Moon system contains special regions called Lagrange points, where the gravitational attractions of Earth and Moon balance in a way that allows small objects to maintain stable or semi-stable positions relative to both bodies. The L4 and L5 Lagrange points, located 60 degrees ahead of and behind the Moon in its orbit around Earth, are theoretically stable locations where material could accumulate over geological time, and some searches have been conducted for dust concentrations at these points. Though results have been inconclusive, the L1 and L2 Lagrange points, located between Earth and Moon and beyond the Moon on the far side respectively, are unstable equilibrium points that are nonetheless useful for spacecraft operations, requiring specific geometrical relationships with both bodies, and they have been proposed as sites for future space infrastructure, including fuel depots, communication relay stations, and the Lunar Gateway space station. The Moon's gravity also contributes to the stability of Earth's orbit around the Sun by participating in the complex gravitational ballet that maintains the orbs. Has produced a rich tradition of scientific observations spanning 4 centuries. In addition to the foundational work of Galileo in the early 17th century, the Moon has been the subject of systematic photographic surveys beginning in the mid-19th century, spectroscopic studies of its surface composition, radar studies of its surface roughness and subsurface structure, and laser-ranging experiments of extraordinary precision. The first photograph of the Moon was taken by John William Draper in 1840, just 5 years after the invention of photography, and subsequent improvements in photographic and optical technology led to increasingly detailed photographic atlases of the lunar surface that served as the primary reference for navigating the Moon until the era of spacecraft. Observation. Radar observations of the Moon, conducted from Earth using powerful transmitters, provided the first information about the large-scale physical properties of the lunar surface, including the depth and characteristics of the regolith layer that would have been important for assessing whether spacecraft could safely land on the lunar surface. The discovery by early radar studies that the Moon's surface had a specific kind of surface roughness at centimeter and meter scales provided the first quantitative constraint on the nature of the regolith and helped allay early fears that the surface might consist of a deep layer of very fine dust into which a landing spacecraft might sink and be swallowed. The tradition of Earth-based lunar science continues today with powerful modern telescopes, sensitive spectrographs, and advanced radar systems contributing to the understanding of the Moon, alongside the flood of data from orbiting spacecraft and the ongoing study of the Apollo samples. The Moon's orbital inclination relative to Earth's equatorial plane varies between about 18 degrees and 28.5 degrees over a period of approximately 18.6 years, a cycle known as the lunar nodal cycle or the Saros series. This variation arises from the precession of the Moon's orbit under the gravitational influences of the Sun and Earth, and it has measurable effects on the strength and character of tides on Earth over the nodal cycle timescale. When the Moon's orbital inclination is at its maximum, the tidal pattern on Earth is subtly different from when the inclination is at its minimum, and these differences can be detected in long tide gauge records. The lunar nodal cycle has been recognized and used by coastal communities and fisheries managers as an important long-period modulation of sea level and tidal patterns. Recent research has suggested that the nodal cycle may also influence long-term variations in rainfall and river flow in some regions, as the subtle changes in tidal forcing interact with ocean circulation patterns in ways that can affect atmospheric moisture transport. The study of the Saros cycle, a period of approximately 18 years 11 days after which the Moon returns to nearly the same position relative to the Sun, Earth, and the lunar nodes, was used by ancient astronomers to predict eclipses with remarkable accuracy. Records of eclipse sequences preserved in ancient Babylonian astronomical tablets demonstrate that astronomers there had identified the Saros cycle at least by the 7th century BCE, and were using it to reliably forecast both solar, lunar eclipses, a sophisticated application of pattern recognition that represents one of the earliest examples of predictive science in human history. The ancient highland terrain of the Moon, the pale and heavily cratered regions that dominate the far side and make up much of the southern near side, contains within it a chemical and isotopic record of events that occurred in the first few 100 million years of the solar system's history. Among the most scientifically significant findings from the analysis of highland rocks returned by the Apollo missions was evidence for a period of greatly elevated impact bombardment that occurred approximately 3.9 billion years ago, a period known as the Late Heavy Bombardment or the Lunar Cataclysm. The evidence for this event includes the clustering of ages of impact, melt rocks from the highlands around 3.9 to 4.0 billion years, a pattern that some scientists have interpreted as indicating that the impact rate in the inner solar system increased dramatically at around this time, before declining to lower levels. The cause of the late heavy bombardment, if it occurred as a discrete event rather than as a gradual tail of the initial bombardment, is thought to be related to an instability in the orbits of the giant outer planets that caused them to migrate to new orbital positions, perturbing the asteroid belt and the Kuiper belt and raining debris onto the inner planets. This event, if real, would have had profound consequences for the early Earth, resurfacing much of the planet and potentially affecting the development of early life. And the timing coincides with the earliest evidence for life on Earth preserved in ancient sedimentary rocks. The question of whether the late heavy bombardment was a discrete cataclysm or a smoother decline in impact rates remains one of the most actively debated topics in planetary science, and new analyses of both Apollo samples and meteorites continue to refine the picture. The light that the Moon reflects toward Earth is sunlight, and the reflectivity of the lunar surface, called its albedo, is relatively low compared to many other solar system objects. The lunar surface reflects only about 12% of the sunlight that falls on it on average, making it considerably darker than snow, which reflects about 80 to 90% of incident light, or even than the soil in a typical terrestrial garden, which typically reflects about 20 to 30%. Despite this low albedo, the full moon appears brilliantly bright in the night sky because it is so close to Earth that even a relatively small percentage of reflected sunlight adds up to a considerable amount of light reaching an observer's eye. The brightness of the full moon varies somewhat depending on the moon's distance from Earth, being about 30% brighter at perigee than at apogee. The moon also appears much brighter when it is high in the sky than when it is near the horizon, partly because atmospheric scattering and absorption reduce the apparent brightness of any celestial object near the horizon, and partly because of the psychological phenomenon known as the moon illusion, in which the moon appears larger and therefore brighter near the horizon than when high in the sky, even though its actual angular size does not change. The moon illusion has been recognized and studied since antiquity and remains a subject of scientific interest in visual perception research, with several competing explanations having been proposed, most of which involve the way the visual system processes apparent size and distance in the presence of reference objects like trees and buildings near the horizon that are absent from the overhead sky. The presence of the moon in Earth's sky has influenced the development of navigation throughout human history. Before the development of accurate mechanical clocks and radio communication, determining longitude at sea was an extraordinarily difficult problem that cost the lives of countless sailors who, unable to determine their east-west position accurately, found themselves wrecked on shores they had not anticipated. The lunar distance method, developed in lunar distance tables required for this method, was itself a major undertaking, requiring the development of a sufficiently precise theory of the moon's motion to allow predictions accurate to better than an arc-minute over years in advance. The effort to develop such a theory, pursued by mathematicians and astronomers across Europe throughout the 18th century, was one of the great intellectual projects of the Enlightenment and produced advances in celestial mechanics that had ramifications throughout mathematics and physics. The lunar distance method was superseded by the invention of accurate marine chronometers and later by radio time signals and GPS, but for nearly a century it served as the primary means by which longitude could be determined far from any coastal landmark. The interior of the moon retains heat from its formation and from the radioactive decay of elements like uranium, thorium, and potassium in its rocks, but the moon has cooled considerably over its 4.5 billion year history, and the heat flow from the interior to the surface today is very small. Apollo 15 and Apollo 17 deployed heat flow experiments that directly measured the rate at which heat escapes from the lunar interior, finding values of about 15 to 20 milliwatts per square meter, roughly half the average heat flow from Earth's interior. This low heat flow reflects the moon's small size relative to Earth and the consequent larger ratio of surface area to volume, which allows heat to escape more readily relative to the total heat stored in the interior. The total heat budget of the moon and the distribution of heat-producing radioactive elements within it are subjects of ongoing investigation, with compositional maps from orbiting gamma-ray spectrometers providing constraints on the global distribution of thorium and other radioactive elements that have revealed an unexpectedly high concentration of these elements in the Prosolarum creep terrain, a geochemically distinctive region of the near side associated with some of the youngest volcanic activity on the moon. Understanding the moon's internal heat budget is important for understanding its volcanic history and the cessation of large-scale volcanism, and it also has implications for understanding how the moon's magnetic dynamo operated and why it eventually ceased. The internal structure of the moon, including the size and state of its core, continues to be refined through analyses of seismic data from the Apollo missions and from more recent passive seismic experiments deployed on the surface. The moon has inspired poets, musicians, and artists throughout recorded history, with a richness of expression that spans every culture and every era. The full moon rising over the landscape has been painted countless times by artists from ancient cave painters to Dutch masters to modern photographers. The crescent moon, delicate and sharp against the evening sky, has appeared on flags and emblems and in jewelry across the ancient and modern world, symbolizing renewal and the passage of time. The moon's association with mystery, with the passage of night, with romance, and with the slower rhythms of time that contrast with the urgency of the solar day, has made it a universal symbol in the literature and music of virtually every civilization. Shakespeare wrote of the inconstant moon that monthly changes in her circled orb. Beethoven wrote his Moonlight Sonata. Debussy composed Clair de Lune. Claude Monet painted the photographs ever taken. The image of Earthrise from the moon, showing Earth as a fragile blue marble against the stark black of space above the grey lunar horizon, became one of the most influential environmental images ever created, helping to catalyze the environmental movement of the 1970s by providing humanity with its first clear visual sense of Earth as a single, unified, bounded object in the vastness of space. The moon's surface is covered by an intricate pattern of ray systems, bright streaks of pulverized and melted rock that extend outward from relatively young impact craters across the darker surfaces of the surrounding terrain. These rays are composed of material ejected at high velocity during the impact event that created the central crater, and they preserve a record of the direction and angle from which the impacting body struck. Because they lie on top of older terrain, and because they are gradually darkened and erased by space weathering processes over time, crater rays are generally associated with geologically young impact structures, and their presence is one of the criteria used to assign craters to the Copernican geological period, the youngest chapter in the Moon's geological history. The ray systems radiating from the crater Tycho near the south pole of the Moon extend across virtually the entire near-side hemisphere and can be seen with the naked eye as bright streaks crossing the Maria. The Tycho crater itself, about 85 kilometers in diameter, was formed by an impact that occurred perhaps 100 million years ago, a geologically recent event by lunar standards. The Surveyor 7 spacecraft landed near the rim of Tycho in 1968 and returned images and chemical data from this young impact terrain, providing a view of relatively fresh impact melt and ejecta material that had not yet been processed by billions of years of space weathering. The study of bright ray craters and their ejecta systems has contributed importantly to the understanding of impact processes and to the calibration of the lunar geological timescale. The thermal properties of the Moon's surface materials have been measured extensively by orbiting spacecraft and by instruments deployed on the surface by the Apollo missions, providing a detailed picture of how the regolith stores and releases heat as the surface cycles through the extreme temperature swings of the lunar day and night. The thermal inertia of the uppermost regolith layer is very low, meaning it heats and cools very quickly in response to changes in illumination. This low thermal inertia arises from the highly porous, loosely packed nature of the fine-grained surface dust, which conducts heat only poorly and stores relatively little heat per unit volume. As a consequence, the surface temperature drops very rapidly after sunset, falling by hundreds of degrees within minutes as the thin layer of sun-warmed dust radiates its stored heat away into space. Beneath the uppermost millimeter or two of surface dust, the temperature stabilizes more quickly because the lower regolith conducts heat even more slowly, and at depths of just a meter or two below the surface, the temperature remains nearly constant at about -35 degrees Celsius, a reflection of the long-term average of solar heating integrated over many years. This stable subsurface temperature was measured directly by heat flow probes driven into the regolith at the Apollo 15 and 17 landing sites, and its value provides a direct measure of the Moon's internal heat flow when combined with the measured thermal conductivity of the regolith. Mapping of the thermal properties of the Moon's surface from orbit has identified regions of anomalously high thermal inertia associated with rock outcrops and large boulders, providing information about the distribution of solid bedrock beneath the surface blanket of fine-grained regolith. The Moon's tidal influence on Earth's rotation and the consequent gradual slowing of Earth's day have been captured in the geological record in several different ways. Ancient tidal rhythmites, sedimentary deposits formed in tidal flat environments where daily tidal cycles deposit alternating layers of sediment, can record the number of daily tidal cycles per lunar month and the number of days per year in the ancient past, providing a direct calendar of Earth's rotational history, extending back hundreds of millions of years. Studies of tidal rhythmites from deposits ranging in age, from modern examples to ancient rocks more than 3 billion years old, have confirmed the gradual lengthening of Earth's day over geological time and have allowed the problems of reconstruction of the historical recession of the Moon from Earth with reasonable precision. Ancient coral reefs also preserve a record of the length of the year and the length of the month in the fine-scale growth banding of coral skeletons, which record daily growth increments as well as monthly and annual patterns. These biological records have been used alongside the physical tidal rhythmite records to extend and corroborate the history of Earth's rotation, inferred from purely physical reasoning about tidal dissipation rates. The agreement between these independent lines of evidence is a satisfying confirmation that the physics governing the tidal interaction between Earth and Moon is well understood, and that the reconstruction of the deep history of the past Earth-Moon system from both physical reasoning and geological observation is a reliable and self-consistent enterprise. These records of the changing length of Earth's day and the recession of the Moon are among the most tangible and directly measurable consequences of the gravitational interaction between Earth and its satellite. The future of the Moon, in the context of Earth's evolving system, will be shaped both by the continuing physical evolution of the Earth-Moon system and by the potential activities of human civilization if it extends its reach to the lunar surface in the coming centuries and millennia. The gradual recession of the Moon will continue at its current rate of a few centimeters per year for the foreseeable future, slowly reducing the apparent angular size of the Moon in Earth's sky, and eventually eliminating the possibility of total solar eclipses. The tidal slowing of Earth's rotation will continue to lengthen the day very gradually, with significant changes occurring only on timescales of hundreds of millions to billions of years. The Sun will eventually enter its red giant phase in about 5 billion years, expanding dramatically and potentially engulfing, or at least severely disrupting the inner solar system, and whatever becomes of Earth and the Moon in that distant future will depend on the details of the Sun's late evolution. On much shorter timescales, measured in centuries and decades, the future of the Moon will be shaped by human choices about exploration, resource utilization, and eventually settlement. The presence of water ice at the poles, the potential for helium-3 mining, the scientific value of the ancient geological record preserved on the lunar surface, and the strategic importance of the Moon as a waypoint for deeper space exploration, all argue for continuing engagement with the Moon as a destination and a resource. The Moon has been a constant companion of life on Earth for more than 4 billion years, shaping the evolution of Earth's climate, the timing of biological rhythms, the development of human culture and science, and the aspirations of explorers and dreamers throughout human history. Its study has contributed and will continue to contribute to the understanding of Earth, the solar system, and the place of life within the cosmos, in ways that remain as compelling in the 21st century as they were when the first human beings gazed upward at its silver light and wondered at the nature of the world beyond their being. The Apollo program's legacy extends through every aspect of space exploration that has followed it. The technologies developed for the lunar landings, from the guidance computers to the life support systems, to the spacesuits to the communication networks, established the technical foundations from which subsequent space programs were built. The scientific knowledge returned by the Apollo missions fundamentally transformed planetary science, establishing the lunar science discipline, revealing the giant impact origin of the Moon, providing the first reliable calibration of the solar system's cratering history, and returning the oldest rock samples available for laboratory analysis anywhere in the solar system. The operational experience gained by NASA in conducting 12 human missions to the Moon and returning all 24 astronauts safely to Earth, despite the enormous complexity of the Saturn V launch vehicles, the Command Service modules, and the lunar modules, proved that human space exploration could be conducted successfully and opened the era of sustained human presence in space that continued with Skylab, Mir, and the International Space Station. The cultural impact of the Apollo program on the generation that lived through it and on subsequent generations who have grown up in its legacy is immeasurable. The image of a human footprint in the lunar dust, made with the full knowledge that it will remain unchanged for millions of years in the absence of any erosional process to erase it, is one of the most potent symbols in the history of human achievement. A mark left not on the surface of Earth, where time will eventually erase all human traces, but on another world, preserved in the geological silence of a body that has been the companion of life on Earth since before life itself began. The orbit of the Moon around Earth is not a simple, stable ellipse, but a complex path that shifts and wobbles under the influence of gravitational perturbations from the Sun, Jupiter, and other bodies in the solar system. The combined effect of all these perturbations means that no two successive orbits of the Moon around Earth are exactly alike. The shape of the orbit changes, the orientation of the orbit in space changes, and the inclination of the orbit relative to Earth's equatorial plane changes, all in response to the varying geometry of the Moon relative to the Sun and the other perturbing bodies. Isaac Newton recognized that explaining the motion of the Moon was one of the hardest problems in celestial mechanics, noting that the Moon's motion made his head ache and kept him awake at night. The development of a sufficiently accurate theory of the Moon's motion required the combined efforts of some of the greatest mathematical minds of the 18th and 19th centuries, including Alexis Claude Clairaut, Leonhard Euler, Jean-Le Rond d'Alembert, Joseph-Louis Lagrange, Pierre-Simon Laplace, and Charles-Eugène Delaunay, each of whom made major contributions to the theory before a fully satisfactory treatment was achieved. The modern theory of the Moon's motion, developed in the 20th century with the aid of computers and confirmed by laser-ranging measurements of extraordinary precision, accounts for hundreds of separate periodic terms in the lunar orbit and can predict the Moon's position to within a few centimeters over timescales of decades. This precision is important not only for planning spacecraft missions but also for fundamental physics, since the laser-ranging data also provide precise tests of general relativity and constrain the rate of change of the gravitational constant and other fundamental quantities. The Moon's surface displays evidence of volcanic activity that operated in a very different manner from the volcanic processes familiar on Earth. On Earth, most volcanism is associated with plate tectonics, occurring at the boundaries between tectonic plates or above hot spots in the mantle. The Moon has no plate tectonics, and its volcanic history was driven entirely by the heat generated by its formation and by radioactive decay in its interior. The volcanic eruptions that created the Lunar Maria were flood basalt eruptions, events in which vast quantities of low-viscosity basaltic magma welled up through fractures in the crust and spread out in broad, thin sheets that filled the floors of large impact basins. These eruptions were not accompanied by the explosive activity that characterizes many terrestrial volcanoes, because the lunar magma contained very little dissolved water and other volatiles that would have driven explosive eruption. The quiet outpouring of fluid basalt produced the smooth, level plains of the mare surfaces, rather than the steep-sided volcanic cones that dominate the landscape around many terrestrial volcanoes. The most recent volcanic activity on the Moon appears to have occurred within the last billion years, and some researchers have proposed that even younger volcanism may have occurred within the last few 100 million years, based on orbital mapping of unusual thermal and morphological features. The volcanic history of the Moon is thus far longer than once believed, extending from the earliest period of the Moon's existence through a prolonged period of basalt flooding in the Maria and potentially persisting in a reduced form nearly to the present geological day. The Lunar Reconnaissance Orbiter camera, operating since 2009, has produced images of the lunar surface at resolutions down to about 0.5 meter per pixel, revealing details of the lunar landscape that were previously invisible. Among the most striking discoveries from these high-resolution images are the presence of pit openings on the lunar surface that may provide access to underground void spaces, possibly ancient lava tubes that formed when the crust of flowing lava solidified around still-flowing lava beneath, which eventually drained away and left behind empty tunnels. Similar lava tubes on Earth range from meters to tens of meters in diameter and can extend for many kilometers. If comparable structures exist on the Moon, which the pit observations suggest is at least possible, they could provide natural sheltered environments for future human habitats, protected from the radiation, micrometeorite impacts, and extreme temperature swings that characterize the open lunar surface. The walls and ceilings of a sufficiently large lava tube would provide shielding equivalent to several meters of solid rock, which would reduce the radiation dose to acceptable levels for long-duration human habitation. Pits that may be skylights into such buried lava tubes have been identified in several regions of the Moon, particularly in the Marius Hills volcanic complex, the Mare Tranquillitatis, and the Mare Ingenii, and their locations have attracted attention as potential sites for future exploration missions that could confirm the existence of subsurface voids and assess their potential utility for human habitation. The Moon's distance from Earth has been measured with increasing precision over the centuries, progressing from the rough geometric estimates of ancient astronomers to the millimeter precision measurements made possible by laser ranging today. The ancient Greek astronomer Hipparchus estimated the Moon's distance at about 60 Earth radii, a remarkably accurate value given the methods available to him. He achieved this using the geometry of a lunar eclipse observed simultaneously from two locations, comparing the timing and appearance of the eclipse from Alexandria in Egypt and from Nicaea in modern Turkey to triangulate the Moon's distance. The development of the telescope in the 17th century allowed more precise angular measurements of the Moon's position, and the introduction of the technique of measuring stellar parallax provided the geometric framework for more accurate distance determinations. The most precise measurements of the lunar distance available today use the laser retroreflectors placed on the surface during the Apollo missions. Laser pulses sent from telescopes on Earth are reflected by these retroreflectors and return to Earth, and the round-trip travel time is measured with such precision that it can determine the Earth-Moon distance to within a few millimeters. 50 years of highly precise distance measurements. The data from this program have confirmed the gradual recession of the Moon, provided precise measurements of the Moon's physical librations, and enabled sensitive tests of fundamental physics, including searches for violations of general relativity and measurements of the Moon's internal structure from its response to tidal forces. The history of robotic spacecraft exploration of the Moon began in the late 1950s and has continued, with only brief interruptions to the present day, producing a body of knowledge about the Moon that would have been impossible to obtain through Earth-based observation alone. The Soviet Lunar program achieved a series of firsts in the history of space exploration. Lunar 1, launched in January 1959, became the first spacecraft to escape Earth's gravity and fly past the Moon, though it missed the Moon and continued into heliocentric orbit. Lunar 2, launched in September of the same year, became the first spacecraft to impact the Moon, crash landing on the surface near the Autolycus crater. Lunar 3, launched in October 1959, became the first spacecraft to photograph the far side of the Moon, returning blurry but revolutionary images of the hemisphere that had never been seen by human eyes. Later missions in the Lunar series achieved the first soft landing on the Moon, the first automated soil analysis, the first automated sample return, and the deployment of the first remotely operated surface rovers, achievements that demonstrated the feasibility of robotic exploration of other worlds long before human visitors arrived. The American Ranger program, which intentionally crash-landed on the Moon while sending back thousands of close-up photographs during the final minutes before impact, provided the first detailed views of the lunar surface at resolutions far better than anything achievable from Earth, revealing the smooth texture of the Mare surface and the omnipresence of small craters at scales invisible from Earth. The thermal history of the Moon, recorded in the ages of rocks from different locations and in the abundance of certain radioactive elements that served as heat sources in the lunar interior, indicates a body that was once far more internally active than it is today. In the earliest period of the Moon's existence, the heat of formation from the giant impact, combined with the heat generated by the intense bombardment of the late accretion period and the radioactive decay of short-lived radioactive isotopes like aluminum-26, kept the Moon's interior hot enough to maintain a global magma ocean for tens of millions of years. As the Moon gradually cooled over the following hundreds of millions of years, the magma ocean solidified from the bottom up and from the outside in, generating the stratified structure of the lunar interior that persists today. The residual heat from the Moon's formation, combined with the ongoing heat generated by the long-lived radioactive decay of uranium, thorium, and potassium, sustained a level of interior warmth sufficient to drive volcanic eruptions and generate the Mare basalts for several billion years. The gradual decline in the rate of heat production as the long-lived radioactive isotopes decayed away, combined with the cooling of the lunar interior by heat conduction to the surface and radiation to space, eventually brought volcanic activity to an end. The timing of the cessation of major lunar volcanism and the question of whether any volcanic activity has occurred in the geologically recent past remains an active area of research, with orbital observations providing evidence for some volcanic features that may be much younger than the bulk of the Mare basalts. The relationship between Earth and the Moon has been one of mutual influence throughout the history of the solar system. The Moon's effect on Earth, through tides and the stabilization of Earth's axial tilt, has already been discussed at length, but Earth has also profoundly influenced the Moon's evolution. Earth's gravity has kept the Moon tidally locked, preventing it from rotating freely. Earth's reflected sunlight illuminates the dark side of the Moon during lunar night, providing a faint but measurable source of light called earthshine that can be seen as the ghostly illumination of the dark portion of the crescent moon visible shortly after new moon. This earthshine, sometimes called the old moon in the new moon's arms, is a romantic sight in the evening sky when the crescent moon is visible in the west just after sunset. Earth's radio and television broadcasts, reflected by artificial satellites, scattered by the atmosphere, and beamed directly into space, have reached the Moon many times over since the first radio signals were broadcast in the early 20th century. Though the Moon is too far away for most of these signals to be detectable there without extremely sensitive equipment. More concretely, human beings have delivered to the Moon's surface hundreds of kilograms of spacecraft hardware, scientific instruments, flags, descent stages, and miscellaneous equipment left behind by the Apollo missions, as well as a small number of personal items and mementos that the astronauts carried with them on their journeys. These human artifacts, sitting on the lunar surface in the silence of the dead regolith, are a tangible expression of the relationship between Earth and the Moon as it entered a new and unprecedented phase in the middle of the 20th century. The minerals found in lunar rocks include many of the same mineral types found in terrestrial rocks, but in proportions and associations that reflect the very different geological history of the lunar mantle. Ilmenite, an iron titanium oxide mineral, is abundant in some of the mare basalts and is one of the primary sources of titanium on the Moon, as well as being a potential source of oxygen through thermal reduction. One mineral that is found on the Moon but is exceedingly rare on Earth is tranquilityite, a complex titanium-zirconium silicate mineral first identified in the Apollo 11 samples from the Sea of Tranquility and for decades considered unique to the Moon. In 2012, small amounts of tranquilityite were identified in ancient igneous rocks in Western Australia, the first confirmed occurrence of this mineral in a terrestrial geological context, demonstrating that the chemical and mineralogical record of the Moon can sometimes provide windows into the deep history of geological processes that also operated on the early Earth, but that have since been erased from the terrestrial geological record by subsequent geological activity. The Moon's surface exhibits a phenomenon called lunar swirls, unusual bright markings on the surface that are associated with localized magnetic anomalies in the underlying crust. These swirls appear as bright, wispy patterns that cut across the darker surrounding terrain, often with complex curvature and internal structure that differs markedly from the branching ray systems of fresh impact craters. The most famous lunar swirl is the Reiner Gamma Formation in Oceanus. Magnetic anomalies associated with lunar swirls is itself debated. One hypothesis holds that they are remnants of a stronger, ancient magnetic field that was locally amplified and preserved in specific rock formations during the time when the global lunar dynamo was still operating. Another hypothesis suggests that they were created by the strong magnetic fields generated in the impact plasma of particularly large meteorite impacts. A third hypothesis proposes that they are associated with the antipodal focusing of seismic energy from large impacts, which compresses and alters the magnetic properties of rocks on the opposite side of the Moon from the impact. The study of lunar swirls continues to provide insights into both the history of the lunar magnetic field and the processes of space weathering that alter the optical properties of airless bodies throughout the solar system. The far side of the Moon, completely hidden from Earth's view and first photographed only in 1959, has a different geological character from the near side that has fascinated planetary scientists since the first images revealed the contrast. The most striking difference is the relative absence of the dark volcanic maria that dominate the near side. The far side is covered almost entirely by ancient, pale-colored highlands terrain, with only a few small, isolated patches of darker volcanic basalt visible in the South Polar region. The South Pole Aitken Basin, the largest and deepest impact basin on the Moon, is centered on the far side and dominates much of the southern hemisphere, yet it contains relatively little volcanic filling compared to the Imbrium and Serenitatis basins on the near side. The reasons for this near-side-far-side asymmetry are not fully understood, but the most widely accepted explanation involves differences in the thickness of the lunar crust between the two hemispheres. The crust on the far side is considerably thicker than on the near side, perhaps by 20 to 30 kilometers on average, and this thicker crust presented a greater barrier to ascending volcanic magma, preventing it from reaching the surface as easily as it did on the near side, where the thinner crust and larger impact basins created favorable conditions for extensive volcanism. The reason for the crustal thickness asymmetry is itself debated, with hypotheses ranging from asymmetric cooling of the lunar magma ocean driven by the thermal influence of a hot early Earth to the coalescence of the Moon from two distinct bodies that merged after they both formed. The exploration of the far side by the Chinese Chang'e 4 rover, operating since January 2019, is providing new surface-level data on this fascinating and previously unexplored terrain. The concept of the Moon as a waypoint for further human exploration of the solar system has gained increasing traction in the early 21st century. The Moon's relatively shallow gravity, well compared to Earth's, means that launching materials from the lunar surface into space requires far less energy than launching the same materials from Earth. If water ice can be extracted from the lunar polar regions in sufficient quantities, it can be electrolyzed using solar power to produce hydrogen and oxygen, the components of the most powerful chemical rocket propellant. A propellant production facility on the Moon could potentially supply fuel for spacecraft traveling to Mars, the asteroid belt, or the outer solar system, dramatically reducing the cost of deep space exploration by allowing spacecraft to refuel in the Earth-Moon system rather than carrying all their propellant from Earth. The Moon also serves as a natural laboratory for testing the technologies and operational procedures that will eventually be needed for Mars exploration. The lunar surface provides extreme conditions of radiation, vacuum, and temperature that are good analogues for the Martian surface, and the relatively short communication time between Earth and Moon, only about 1¼ seconds at the speed of light, compared to the several minutes to tens of minutes for Earth-Mars communication, makes it easier to provide real-time support from Earth to lunar surface operations. Spending extended periods on the Moon's surface would also allow the medical and physiological effects of reduced gravity on the human body to be studied over timescales of months and years, providing data that could be used to design health countermeasures for Mars missions. The Moon is thus seen not only as a destination in its own right, but as the first step in a longer journey of human expansion into the solar system. The regolith of the Moon contains iron in several forms, including iron incorporated into silicate minerals, iron in the form of rust-like oxide minerals like ilmenite, and pure metallic iron in the form of tiny grains dispersed throughout the soil. This metallic iron in the lunar soil is not the product of terrestrial-style oxidation and reduction cycles, but rather arises from two distinct sources. Some of it derives from the iron in meteorites that have struck the Moon over billions of years, contributing metal from the impactor bodies to the fine-grained soil matrix. Some of it is produced by the solar wind, which reduces iron from the mineral surfaces of soil grains through the process of ion bombardment, leaving small metallic iron particles coated onto the surfaces of the individual grains. This ubiquitous metallic iron, called nanophase iron or simply nanophase iron, is one of the primary causes of the optical darkening associated with space weathering. It absorbs light very efficiently at all visible wavelengths and gives the space-weathered lunar soil its characteristically gray appearance. The presence of nanophase iron also makes the lunar soil weakly magnetic, which is somewhat surprising given that the bulk of the lunar soil is composed of non-magnetic silicate minerals. This weak but measurable magnetism allows the soil to respond to external magnetic fields, and early proposals for lunar resource utilization suggested that magnetic separation might be used to concentrate the metal-bearing soil particles for processing. The study of nanophase iron in lunar soil and in the regolith of other airless bodies in the solar system has become an active area of remote sensing research, since the abundance and form of nanophase iron is a sensitive indicator of the degree of space weathering that a surface has experienced. The Moon has been observed during and after solar eclipses in ways that have contributed important scientific knowledge about both the Moon and the Sunday. During total solar eclipses, when the Moon completely blocks the solar disk, the chromosphere and corona of the Sun become visible, and the Moon's limb provides a sharp edge against which the structures of these outer solar layers can be observed with great clarity. The first measurements of the speed of sound in the solar atmosphere, derived from observations of the chromospheric spectrum during eclipse totality, were made possible by the Moon's precise blocking of the photosphere. The first spectroscopic identification of helium in any context was made during the solar eclipse of 1868, when the French astronomer Jules Janssen observed an unknown yellow line in the chromospheric spectrum, and the English astronomer Norman Pogson independently identified the same line at the same eclipse. The element was subsequently named helium, after Helios, the Greek god of the sun, because it was identified in the solar atmosphere before it was discovered on Earth. The Moon's shadow during total solar eclipses also creates sudden cooling and other atmospheric effects that have been studied as natural experiments in atmospheric science. Animals and plants respond to the sudden darkness, temperature drop, and change in electromagnetic conditions during totality in ways that provide insights into the environmental triggers for various biological behaviors. The path of totality for any given solar eclipse is narrow, typically only 100 to a few hundred kilometers wide, so the experience of witnessing totality is both geographically and temporally constrained, making the planning and travel required to observe total solar eclipses a significant undertaking for professional and amateur astronomers alike. The Moon's chemical composition, determined from laboratory analysis of the images that reflect the specific processes involved in its formation and early evolution. The Moon is depleted in volatile elements, those that boil or evaporate at relatively low temperatures compared to the bulk composition of Earth. Elements like sodium, potassium, sulfur, and the noble gases are all less abundant on the Moon than on Earth, a depletion that is consistent with the high temperatures and energies associated with the giant impact event that is thought to have formed the Moon. On the other hand, the Moon is enriched in refractory elements, those that vaporize only at very high temperatures, which concentrated in the cooling aftermath of the impact. The Moon is also enriched relative to Earth in iron oxides and depleted in metallic iron, a compositional difference that reflects the fact that the Moon formed primarily from the mantle material of both Earth and the impactor, rather than from their iron-rich cores, which remained behind in the merged body that became Earth. The isotopic composition of the Moon is strikingly similar to that of Earth's mantle for many elements, including oxygen, which has 3 stable isotopes that occur in characteristic ratios in materials from different parts of the solar system. This isotopic similarity implies either that the Moon formed from material that was compositionally very similar to Earth's mantle, regardless of its ultimate source, or that the materials from Earth's mantle and the impactor Theia were efficiently mixed during the impact before the Moon-forming debris disk separated from the combined system. The surface of the Moon is divided into 2 primary terrain types that are immediately distinguishable even to the naked eye: the pale, heavily cratered highlands and the darker, smoother volcanic plains of the Maria. These two terrain types differ not only in their appearance and age, but also in their elevation, composition, and the processes that shape them. The highlands stand on average about 4 kilometers higher than the mare plains, a difference in elevation that reflects in part the thicker crust beneath the highlands and in part the filling of the large impact basins by volcanic basalt that created the lower-lying mare plains. The surface roughness of the two terrain types also differs dramatically at all scales. The highlands are rough, complex, and saturated with craters of all sizes, while the Maria are comparatively smooth and flat, with a lower density of craters, reflecting their younger age and the shorter time available for subsequent bombardment. The compositional differences between highlands and Maria, measured by orbital gamma-ray spectrometers and confirmed by sample analysis, are equally striking. Highland rocks are rich in calcium and aluminum, reflecting the predominance of plagioclase feldspar in the ancient anorthosite crust. Mare basalts are richer in iron, magnesium, and titanium, elements that are more abundant in the deep mantle material from which the volcanic magma was derived. The study of the chemical mapping of the Moon from orbit has allowed the construction of global element abundance maps that reveal systematic compositional variations across the surface at regional scales, providing constraints on the structure of the lunar interior and the processes of differentiation that shaped it during the first billion years of the Moon's existence. The question of how the Moon came to have such low density relative to Earth has been a central issue in theories of lunar origin since the question was first seriously addressed in the 19th century. The Moon's average density of about 3,300 kilograms per cubic meter is noticeably lower than Earth's average density of about 5,500 kilograms per cubic meter, a difference that implies the Moon contains a lower proportion of dense iron than Earth. If the Moon had the same bulk composition as Earth, its density would be closer to that of Earth, so the Moon must be systematically depleted in iron relative to Earth. The giant impact hypothesis explains this iron depletion naturally. When Theia struck the proto-Earth, both bodies were already differentiated into iron cores and silicate mantles, and the material that was ejected into orbit to form the Moon came predominantly from the silicate mantles of the two bodies, rather than from their iron cores, which were too deep and too massive to be significantly excavated by the impact. The Moon thus formed from material that was already depleted in iron relative to the bulk composition of either Earth or Theia, explaining its lower density. This story is consistent with the compositional data from the Apollo samples and with computer models of the giant impact event, though the details of exactly how the ejected material was partitioned between the Moon-forming disk and the residual Earth have been the subject of many subsequent refinements, as numerical models of the impact have improved in resolution and physical realism over the decades since the giant impact hypothesis was first proposed in 1975. The Moon's surface bears the marks of impacts not only from random asteroids and comets, but also from the directed shower of ejecta from specific large impacts elsewhere on the Moon. When a very large asteroid strikes the Moon, the explosion that results throws material outward at high velocities in all directions, and some of this material can travel all the way around the Moon or even escape into space temporarily before falling back in a distributed pattern. The most extreme case of this kind of ejecta redistribution is seen in the antipodal terrain of large impact basins, the region of the lunar surface directly opposite the basin center. Here, the seismic energy from the impact and the focusing of ejecta returning from space after escaping the Moon temporarily can produce unusual terrain features that record the extraordinary violence of the original impact in a location far removed from the impact site itself. The chaotic terrain on the far side of the Moon, opposite the Caloris Basin on Mercury, is a famous example of this kind of antipodal impact effect on an airless body, and similar features have been identified on the Moon at the antipodes of some of the largest impact basins. The study of how impact ejecta is distributed across the lunar surface has important implications for understanding the mixing and homogenization of the lunar regolith over geological time, for interpreting the compositions measured in the lunar soil at any given location, and for planning future sample return missions, whose goal is to obtain samples representative of specific geological units, rather than mixtures containing material transported from distant locations by the cumulative effects of billions of years of impact ejecta deposition. The history of how the Moon's shape and internal structure were determined is a story of ingenious scientific detective work spanning more than 2 centuries. The first accurate determination of the Moon's overall size and shape was achieved by ancient Greek astronomers using geometric methods involving the observation of lunar eclipses and solar eclipses. Aristarchus of Samos, working in the 3rd century BCE, developed a method for measuring the relative distances to the Moon and Sun using the geometry of quarter moon phases and lunar eclipses, obtaining values that were not precise. The Apollo Seismic Network, consisting of instruments placed at the Apollo 12, 14, 15, and 16 landing sites, recorded thousands of seismic events over several years of operation, providing data that were used to infer the depth of the lunar crust, the existence and properties of the lunar mantle, and the size and state of the lunar core. More recently, the Grail mission of 2011 and 12 used 2 small spacecraft flying in formation around the Moon to map its gravity field in extraordinary detail, revealing density variations within the lunar crust and mantle that provide information about the internal structure far beyond what the Apollo seismic data alone could provide. The Moon's role in the development of scientific thought about the nature of the cosmos is difficult to overstate. From ancient times through the scientific revolution of the 16th and 17th centuries, the Moon occupied a unique position in human thinking about the universe as the nearest body beyond Earth and the most detailed and observable example of a world other than our own. The observation by Galileo that the Moon had mountains and craters and plains, that it was a world with complex topography rather than a smooth crystalline sphere as ancient and medieval thinkers had believed, was one of the most revolutionary findings of the early telescopic era and contributed substantially to the overthrow of the Aristotelian model of the cosmos that had dominated European intellectual life for more than 1,000 years. The subsequent detailed mapping of the Moon's surface by Hevelius, Riccioli, and other 17th century astronomers established the discipline of observational lunar science and demonstrated that systematic study of a celestial body could produce reliable, reproducible, and increasingly detailed knowledge of its physical character. Isaac Newton's successful explanation of the Moon's orbital motion, using the same gravitational law that governed the fall of objects on Earth's surface, was one of the defining achievements of the scientific revolution, demonstrating that the physical laws governing the heavens were the same as those governing motion on Earth, and thus unifying the terrestrial and celestial realms in a single coherent physical framework. The Moon has thus served throughout the history of science as both a subject of investigation in its own right and as a testing ground for developing and applying the physical theories that have progressively deepened human understanding of the universe as a whole. The Chinese space program's exploration of the Moon in the early 21st century has provided a series of new datasets and capabilities that have enriched the scientific understanding of the lunar surface. The Chang'e 1 mission, launched in 2007, provided China's first global map of the lunar surface from orbit and tested the key technologies for subsequent more ambitious missions. Chang'e 2, launched in 2010, achieved higher resolution mapping and then departed lunar orbit to fly by the asteroid Tutatis, demonstrating China's capability to extend robotic missions beyond the Earth-Moon system. Chang'e 3, launched in 2013, deployed the U2 rover on the surface in the Mare Imbrium and made important compositional measurements of a type of basalt that had not previously been sampled directly. Chang'e of terrain that had never been visited before. Chang'e 5, launched in November 2020, achieved a soft landing in the Oceanus Procellarum region, collected about 1.7 kilograms of lunar soil and rock samples from a previously unsampled location, and returned them to Earth in December 2020, making China only the third nation to return samples from the Moon after the United States and the Soviet Union. The analysis of these samples has provided new information about the age of volcanism in the Procellarum region and the isotopic composition of the youngest sampled lunar basalts. The idea that the Moon might harbor life, or even intelligent life, persisted in popular imagination and to some extent in scientific discourse well into the 19th century. The astronomer William Herschel, who discovered the planet Uranus and made many other major contributions to astronomy, believed that the Moon was likely inhabited, citing the presence of features he interpreted as forests and the general principle that the Creator would not have made such a world without populating it. The famous moon hoax of 1835, published in the New York Sun newspaper and falsely attributed to the astronomer John Herschel, described a series of spectacular observations supposedly made with a powerful new telescope that revealed the Moon to be populated by bat-winged humanoid creatures, giant beavers, and bison-like animals living near a sapphire blue ocean. The articles were widely believed and sparked enormous public excitement before being revealed as a complete fabrication. Even as late as the early 20th century, some reputable scientists maintained that life on the Moon was not impossible, pointing to apparent changes in surface markings as evidence for vegetation that responded to the light and warmth of the lunar day. The first spacecraft observations, and eventually the Apollo missions, settled the question definitively: the Moon is utterly lifeless. No organism of any kind has ever been found in the lunar samples, and the environmental conditions of the lunar surface, with its extreme temperature swings, absence of liquid water and atmosphere, and constant bombardment by ultraviolet radiation and cosmic rays, are incompatible with any known form of life. The question of whether life could persist in the permanently shadowed regions near the poles, protected from radiation by the surrounding crater walls, has been raised, but is considered extremely unlikely given the complete absence of any other life-sustaining conditions. The Moon's polar regions have attracted growing scientific attention in recent years, not only because of the water, ice, and other volatiles they contain, but also because of the unique scientific information encoded in the permanently shadowed terrain. The permanently shadowed craters near the poles have been cold enough to trap and preserve volatile materials for potentially billions of years, creating a kind of cosmic time capsule in which the delivery of volatiles to the Moon by comets, asteroids, and the solar wind over geological time has been recorded. The ratio of different isotopes of hydrogen in the lunar polar ice, for example, could provide information about the relative contributions of comets and asteroid impacts to the Moon's water inventory, since these two sources of water have different deuterium to hydrogen ratios that can, in principle, be distinguished by precise isotopic measurements. The organic molecules present in the polar volatile deposits could provide information about the types of complex organic chemistry that occur in comets and asteroids, and that may have contributed organic precursors to the early Earth at text. At the same time, they were delivering water and other volatiles to the Moon. The exploration of the permanently shadowed regions presents extraordinary engineering challenges because any lander or rover operating in these regions must function in complete darkness at temperatures approaching -240 degrees Celsius, without access to solar power, and in a radiation environment altered by the absence of solar wind. Future missions designed to explore these regions will need to carry their own power sources, rely on communication relays to maintain contact with Earth, and be designed to withstand the extreme cold that would challenge the operation of every electronic and mechanical component. The surface of the Moon is marked at many locations by clusters of small, irregular depressions that were long interpreted as volcanic cinder cones or maars, but have more recently been recognized as secondary impact craters, produced by large fragments of ejecta from primary impact craters that struck the surface at lower velocities than primary impactors and produced distinctive morphologies that differ from the regular circular forms of primary impact craters. These secondary craters often occur in chains or clusters along rays extending from primary craters, providing a geometric fingerprint that allows them to be identified even when they are not immediately adjacent to an obvious ray system. Understanding the distinction between primary and secondary impact craters is important for the accurate dating of lunar surfaces using crater counting techniques, because the apparent age of a surface could be significantly overestimated if large numbers of secondary craters were counted as primary impacts and used to calculate the impact flux. The contribution of secondary craters to the total crater population on the Moon's surface at different size scales has been a subject of considerable debate among planetary scientists, with some arguing that secondary craters dominate at small sizes and others contending that their contribution has been overestimated. Resolving this debate is important not only for dating lunar surfaces accurately, but also for applying crater-based dating methods to other planetary surfaces in the solar system, where the secondary to primary crater ratio may be different from the Moon's due to the different surface gravity and atmospheric conditions on other worlds. The Moon's mass has been determined with great precision from the measurement of its gravitational influence on objects in its vicinity, including the Apollo Command and Service modules in lunar orbit, unmanned spacecraft orbiting the Moon, and the laser-ranging experiments that track the orbital motion of the Moon itself around Earth. The most precise determinations of the Moon's total mass come from the Grail mission, which tracked two small spacecraft in close lunar orbit and measured the tiny accelerations they experienced due to local variations in the lunar gravity field. From the total gravitational influence of the Moon, the total mass can be calculated precisely. Combined with the precisely known volume of the Moon derived from laser altimetry and imaging, the average density of the Moon is determined to be about 3,346 kilograms per cubic meter. This density, when compared to the known densities and compositions of various rock types, confirms that the bulk of the Moon is composed of silicate rocks similar to the mantle of Earth, with a small, dense core making up only 1 to 2% of the Moon's total mass, compared to Earth's core, which makes up about 30% of Earth's total mass by volume. The smallness of the lunar core is consistent with the giant impact hypothesis for the Moon's formation, and is one of the key compositional constraints that any successful theory of the Moon's origin must explain. The distribution of mass within the Moon, including systematic offsets between the Moon's center of mass and its center of figure, has also been inferred from the Grail gravity data and provides important constraints on the internal density distribution and the history of the Moon's thermal and mechanical evolution. The geological record of the Moon provides information about the solar system's early history that is unavailable from any other accessible source, because the Moon lacks the geological and atmospheric processes that have erased the equivalent record from Earth's surface. The most ancient chapter of solar system history, spanning the first few 100 million years after the planets formed, is documented on the Moon in the heavily cratered surface of the highlands, in the ages of the oldest lunar rocks, and in the composition of the regolith that has accumulated the chemical signatures of billions of years of bombardment and solar wind implantation. The study of the Moon's ancient record has contributed directly to the understanding of how the inner solar system evolved from the chaotic, debris-filled environment of the early solar system to the relatively quiescent state it inhabits today. Among the most important contributions has been the calibration of the impact flux, the rate at which asteroids and comets struck the Moon, and by extension the other inner planets, as a function of time. This calibration, derived from the measured ages of impact, melt rocks and basalts at different depths in the regolith, provides the timescale for understanding when surfaces of different crater densities on the Moon, Mars, Mercury, and other bodies formed, allowing the geological histories of these worlds to be read from their crater populations. The extension of this chronology beyond the Moon to other planets depends on assumptions about how the impact rate varied with heliocentric distance and has been the subject of ongoing refinement as new data from spacecraft missions to Mars, Mercury, and the asteroids have become available. The night sky as seen from the Moon is a dramatically different experience from the night sky as seen from Earth. Because the Moon has no atmosphere to scatter light, the sky above the lunar surface is always perfectly black, even in the fully sunlit daytime hemisphere. The stars are visible at all times regardless of whether the sun is above or below the horizon, though of course no observer can look directly at the sun without risking serious eye injury. The stars do not twinkle, because the twinkling of stars as seen from Earth is caused entirely by the refraction and scattering of starlight by Earth's turbulent atmosphere, an effect absent on the airless Moon. The constellations as seen from the Moon are identical to those seen from Earth, because the Moon is close enough to Earth on the scale of the distances to even the nearest stars that the shift in perspective between the two viewpoints is completely negligible. Earth itself hangs in the lunar sky as a brilliant blue and white sphere, appearing about 4 times larger in angular diameter than the Moon, appears from Earth's surface and displaying its own cycle of phases as the geometry between Earth, the Moon, and the Sun changes. Earth in the lunar sky goes through its phases in the reverse sequence from the Moon's phases as seen from Earth. When the Moon is full, as seen from Earth, Earth appears as a new Earth as seen from the Moon, showing only the dark side toward the lunar observer. The brilliance of the fully lit Earth as seen from the Moon is extraordinary, many times brighter than the full Moon appears from Earth, and the swirling cloud patterns, blue oceans, and brown and green land masses of Earth provide a continuously changing view of the home planet that would surely be among the most affecting and perspective-altering sights available to any human being who might one day stand on the lunar surface and gaze homeward. The Moon's surface gravity, while only 1/6 that of Earth, is strong enough to hold the fragile exosphere of gas molecules that constitutes the lunar atmosphere and to maintain the positions of everything sitting on the surface. From the massive ancient mountains to the finest grains of dust, the mathematics of gravity on the lunar surface are simple and elegant. An object dropped from a height on the lunar surface falls with an acceleration of 1.6 meters per second squared, meaning it gains speed at a rate that is about 6 times slower than a falling object on Earth. A ball thrown upward on the Moon will rise about 6 times as high as the same throw would produce on Earth, and it will take about 6 times as long to come back down. The escape velocity from the Moon's surface, the minimum speed needed to overcome lunar gravity entirely and escape into space without further propulsion, is about 2.4 kilometers per second, compared to 11.2 kilometers per second for Earth. This lower escape velocity is one of the reasons why the Moon is considered an attractive location for launching materials into space. A spacecraft leaving the Moon needs far less energy to reach Earth orbit or even escape the Earth-Moon system entirely than a spacecraft launching from Earth's surface. The implications of this fact for the economics of space exploration have been recognized since the early days of the space age, and proposals for using the Moon as a launch facility or as a source of materials that could be launched into space at lower cost than equivalent materials from Earth's surface have been a recurring theme in discussions of future space development ever since. The physics of gravity on the Moon also govern the behavior of ejecta from impacts, of volcanic eruptions that may have occurred in the past, and of the gentle gravitational settling of the regolith over geological timescales. The Moon's orbit precesses in space, meaning the orientation of the elliptical orbit slowly rotates over time like a spinning top. One type of precession, the precession of the line of apsides, is the rotation of the long axis of the orbital ellipse, which means that the positions of perigee and apogee in the Moon's orbit shift slowly from month to month relative to the fixed stars. The complete cycle of the apsidal precession takes about 8.85 years. Another type of precession, the precession of the line of nodes, is the rotation of the points where the Moon's orbit intersects the plane of the ecliptic, which are the 2 points in the Moon's orbit where solar and lunar eclipses can occur. The nodal precession completes a full cycle in about 18.6 years, and it is this precession that is responsible for the slow shifting of the pattern of eclipse seasons from year to year. These various precessions of the Moon's orbit are caused by the gravitational influences of the Sun, the oblateness of Earth, and, to lesser extents, the planets and other bodies of the solar system, and they have been studied and modeled with great precision over centuries of astronomical observation. The effects of the nodal precession on Earth's climate have been studied as well, since the variation in the Moon's orbital inclination caused by this precession affects the pattern of tidal forcing on Earth's oceans, which in turn can influence atmospheric circulation and precipitation in subtle but measurable ways. The nodal precession cycle of 18.6 years has been identified in climate records from various parts of the world, including rainfall patterns, river flow data, and coral growth records, suggesting that the lunar orbital geometry is indeed a detectable influence on Earth's climate system at this timescale. The exploration of the Moon by astronauts during the Apollo program revealed a landscape of stark and timeless beauty that all 12 people who walked on it described in vivid terms. The astronauts uniformly reported being struck by the complete silence of the Moon, a silence so absolute and so unfamiliar that it required adjustment by people accustomed to the constant ambient sounds of life on Earth. They described the ground beneath their feet as varying from a firm, packed surface in some places to a soft, powdery layer several centimeters deep in others, with the fine dust kicked up by their footsteps drifting in the absence of air only under the influence of the low lunar gravity before settling back to the surface. The contrast between the inky black sky and the brilliantly sunlit landscape created a visual environment unlike anything on Earth, with no gradation of light and shadow in the sky, no blue to soften the transition between lit and dark regions, and shadows of extraordinary sharpness and depth. The Earth hanging in the black sky, beautiful sight they had ever seen. Several of the astronauts described a profound sense of connection to human history and to the entirety of human civilization that they carried with them on the surface. A feeling that they were representing not just themselves or their country, but the whole of humanity in taking those first steps away from the home planet onto another world. The words spoken by Neil Armstrong upon becoming the first human being to set foot on the moon, that it was one small step for a man, but one giant leap for mankind, captured this sense of historical significance in a phrase that has entered the permanent vocabulary of human civilization. The process by which the moon's cratered surface was produced involves physics that scientists have studied, both through observation of the moon and through laboratory experiments using high-velocity impact guns to simulate collisions on a small scale. When a meteorite traveling at many kilometers per second strikes the lunar surface, the initial contact produces pressures of millions of atmospheres, compressing both the impactor and the target rock to extreme densities and heating them to temperatures of thousands of degrees. The impactor is essentially vaporized in a fraction of a second, and the enormous energy released propagates outward as a powerful shock wave that fractures the surrounding rock and excavates a cavity that grows rapidly as the shocked material is expelled. The final crater is much larger than the original impactor, with typical ratios of crater diameter to impactor diameter ranging from about 10:1 for small impacts to 20:1 or more for larger impacts, depending on the velocity, composition, and angle of the impacting body. The material expelled from the crater, called ejecta, is thrown outward in all directions and lands in a roughly circular deposit around the crater whose thickness decreases with distance from the crater rim. The largest blocks in the ejecta, too large to be completely destroyed by the impact, land near the crater and form the hummocky, rough terrain of the crater's ejecta blanket. Finer material is thrown at higher angles and higher velocities, reaching greater distances from the crater and forming the bright rays visible around young craters. A significant fraction of the ejecta escapes the moon entirely if the impact is large enough, becoming meteorites in space that may eventually fall on other bodies in the solar system. The study of impact mechanics has been transformed by detailed analysis of the moon's cratered surface, with the moon providing a permanent and undisturbed record of impacts at every scale, from the tiniest micrometeorite pits to the enormous multi-ring basins thousands of kilometers in diameter. The moon is the subject of a rich tradition of scientific observation conducted not by professional astronomers in major observatories but by amateur astronomers, citizen scientists, and dedicated hobbyists who observe the moon from backyard telescopes and report their observations to organizations that compile and analyze the accumulated data. Amateur observers have made genuine contributions to lunar science, particularly in the area of detecting and recording transient lunar phenomena, brief flashes of light, or apparent color changes on the lunar surface that may indicate ongoing outgassing or impact events. While many reported transient lunar phenomena have turned out to have mundane explanations such as glints of sunlight off mountain peaks or artifacts of atmospheric distortion in the Earth-based telescopes used to observe them, some appear to be genuine surface events whose causes are still debated. The bombardment of the lunar surface by small meteorites continues at a measurable rate even today, and these small impacts produce brief flashes of light that are occasionally visible through telescopes from Earth or that can be detected by video cameras attached to telescopes and automated to watch for such events. The Apollo seismic network detected many such small impacts, providing a statistical picture of the current small body impact rate at the moon that is consistent with independent estimates from telescopic monitoring. The tradition of amateur observation of the moon extends back to the dawn of the telescopic era, and the lunar maps produced by 17th and 18th century amateur and semi-professional observers provided the foundation for the professional maps that guided the planning of the Apollo missions. The Moore Foundation's systematic photographic lunar atlas of the 20th century and similar projects demonstrate the level of quality achievable by dedicated amateur observers using equipment available to individuals rather than institutions. The Moon has been the target of proposals for a wide range of economic activities beyond simple exploration, including the mining of helium-3 for fusion fuel, the extraction of rare earth elements and other materials of economic value, the establishment of tourism facilities, and the siting of large radio telescope arrays on the far side of the Moon, where they would be shielded from the radio frequency interference generated by human civilization on Earth. The Far Side Telescope proposal is particularly scientifically compelling because the radio frequency environment on the far side of the Moon, completely shielded from Earth-generated interference by the entire bulk of the Moon, would allow observations at very low radio frequencies that are blocked by Earth's ionosphere and overwhelmed by human-generated radio noise when attempted from Earth's surface or even from low Earth orbit. A radio telescope operating in this frequency side is thus seen by radio astronomers as potentially the most valuable piece of astronomical real estate in the solar system, a location where a major observatory could address fundamental questions about the nature and evolution of the universe that cannot be answered from any other accessible vantage point. The Moon's appearance changes throughout the lunar month in ways that have inspired detailed observation and measurement since the earliest development of systematic astronomy. The waxing and waning of the Moon's phases, from the thin crescent visible shortly after new moon through the full moon to the thin waning crescent before the next new moon, is one of the most regular and predictable of all natural cycles, and its reliability has made it the basis of timekeeping systems in cultures around the world from the earliest times. The exact shape and orientation of the crescent moon visible in the evening sky after new moon varies systematically with the season, being nearly horizontal in tropical and subtropical latitudes in spring, when the ecliptic is steeply inclined to the horizon, and more steeply inclined in autumn, when the ecliptic makes a shallower angle with the horizon. These seasonal variations in the appearance of the young crescent moon have been noted and used for practical purposes in different cultural traditions, particularly in the Islamic world, where the determination of the start of each month by the first sighting of the crescent moon after new moon has required careful attention to these seasonal and geographic variations that differs from its perceived behavior. The Moon's influence on human biology has been a subject of popular belief and scientific investigation throughout history. The word lunacy, derived from the Latin word for the moon, reflects the ancient belief that the full moon affected mental states and behavior, a belief that persists in many forms in popular culture today. The scientific evidence for direct effects of the full moon on human behavior is largely negative. Extensive analyses of hospital admissions, accident rates, criminal behavior, and other metrics across large populations have generally failed to find convincing correlations with the lunar phase that could not be explained by other factors. The sleep of individuals does vary with the lunar cycle in some studies, with the full moon period being associated with slightly shorter sleep duration and reduced sleep quality in some controlled laboratory experiments conducted under conditions where subjects could not see the moon or know what phase it was, suggesting a possible biological rhythm that responds to the lunar cycle through some mechanism other than simple light exposure. The biological mechanisms for such effects are not well understood, and the effect sizes reported are small. Whether human circadian rhythms retain a vestigial sensitivity to the lunar cycle from an ancestral period before artificial lighting disrupted the natural light environment is a hypothesis that has attracted some scientific interest, without yet producing a consensus. The influence of the moon on the behavior of other organisms is much better established, with many marine species showing clear synchronization of reproductive and behavioral cycles with the lunar calendar, and the question of whether human biology retains traces of similar sensitivity is an interesting one that warrants continued careful investigation. The thermal emission from the lunar surface, measured by sensitive infrared detectors aboard orbiting spacecraft, provides a global view of the temperature distribution across the Moon's surface that complements the radar and optical observations from the same platforms. The pattern of thermal emission closely tracks the pattern of solar illumination, with temperatures highest on the sunlit surface near the subsolar point and lowest in the permanently shadowed polar craters. But deviations from this simple pattern reveal interesting information about local surface properties. Areas of unusually high thermal emission, called thermal anomalies, may indicate regions where the subsurface temperature is elevated by localized heat sources, such as concentrations of radioactive elements or residual geothermal heat from ancient volcanic activity. Areas of unusually low thermal emission in otherwise sunlit regions may indicate the presence of exposed bedrock or areas where the regolith has been disturbed, since fresh, unweathered rock has different thermal properties than the well-processed regolith. The distribution of large boulders on the lunar surface, which appear as warm spots in nighttime thermal images because they retain heat from the day much better than the fine-grained regolith, can be mapped across the entire Moon using thermal infrared data from orbiting spacecraft, providing information about the locations of recent impacts and the regional variability in the abundance of surface rocks. The monitoring of thermal anomalies on the Moon over time could potentially reveal changes in surface conditions or detect new impact events, adding a temporal dimension to the understanding of the Moon's surface environment that complements the static information available from high-resolution optical imaging. The study of lunar meteorites found on Earth has extended the sampling of the Moon far beyond the 6 Apollo landing sites and the 3 Soviet lunar sample return sites, providing glimpses of terrain types and geological units that were not visited by any of these missions. Lunar meteorites are identified by their characteristic compositions, which are distinctly different from terrestrial rocks and from the more common stony meteorites derived from asteroids, and by the cosmic ray exposure ages that indicate they spent time traveling through space before landing on Earth. They are found primarily in Antarctica and in hot desert regions of Africa, Australia, and the Arabian Peninsula, where the contrasting color of the pale, rocky meteorites against the surrounding terrain makes them easier to locate than in most other environments. The compositional diversity of the known lunar meteorite collection is impressive, with specimens representing ancient highland anorthosite, mare basalts, from locations spanning a wide range of compositions and ages, and various types of impact melt and breccia formed by the large impacts that have shaped the lunar surface over billions of years. Some lunar meteorites provide information about the composition of specific geological units on the lunar surface that can be identified from orbit, allowing the composition measured in hand samples to be connected to the specific surface units mapped by orbital spectroscopy. The paired study of lunar meteorites and orbital spectroscopic data has been one of the most productive synergies in post-Apollo lunar science, allowing the compositional information available from the limited number of sample return sites to be extended to a global picture of the Moon's surface composition, using the much more comprehensive coverage available from orbiting spacecraft. The Moon has been used as a natural retroreflector for radar signals since the early 1940s, when engineers first bounced radar pulses off the Moon and received the return signal, a demonstration that became known as moon bounce, or Earth-Moon-Earth communication. This technique, which exploits the Moon's large physical cross-section as a passive reflector, has been used both for scientific purposes such as measuring the Earth-Moon distance and mapping the surface roughness of the Moon, and for practical communication purposes, allowing radio signals to be relayed over great distances by reflecting them off the Moon. The very long path length and the inverse square law reduction in signal strength over the Earth-Moon-Earth path makes moon-bounce communication technically challenging and energy-intensive, requiring high-power transmitters and large antennas, but it has the advantage of being completely independent of satellites or any artificial infrastructure beyond the two communication stations themselves. Amateur radio operators have made use of moon-bounce communication for decades, bouncing signals off the Moon to communicate with other ham radio stations on the far side of Earth in situations where ionospheric propagation or satellite links are not available. The radar studies of the Moon conducted since the 1940s have contributed substantially to the understanding of the physical properties of the lunar surface, including the depth and density profile of the regolith, the roughness of the surface at centimeter and meter scales, and the dielectric properties of the lunar soil, all of which were important inputs for the engineering design of the Apollo lunar modules and the planning of the first lunar landings. The Moon's distance from Earth varies continuously in a predictable way that can be calculated far into the future using the known equations of gravitational dynamics. At any given moment, the exact distance to the Moon is a function of where the Moon is in its elliptical orbit, how that orbit is currently oriented in space, and the cumulative gravitational perturbations from the Sun and other bodies that have acted on the orbit since some reference time. For most practical purposes, the Moon's distance can be treated as varying smoothly between approximately 356,000 kilometers at perigee and 406,000 kilometers at apogee, with the exact values at any given moment depending on where the Moon is in its roughly 27-day anomalistic month, the period from one perigee to the next. The combination of the monthly variation in distance with the multi-year modulation of the orbital eccentricity, which affects how large the perigee-apogee distance difference is at any given time, produces a rich variety of apparent moon sizes over time that amateur astronomers who pay attention to the angular size of the Moon can detect by careful measurement or falls near perigee, has captured the attention of both the astronomical community and the general public, leading to extensive public education efforts aimed at explaining the relatively modest nature of the size and brightness enhancement associated with supermoon events, while acknowledging that these events do provide a genuine, if subtle, increase in the Moon's apparent size and brightness compared to a full moon occurring near apogee. The ancient geological record preserved on the Moon's highland surface contains minerals that formed under conditions very different from those prevailing at the lunar surface today. Among the most intriguing of these minerals are those that show evidence of having crystallized in the presence of water or other volatile materials at some early stage of their history before the Moon became the dry, airless body it is today. The discovery of traces of water in volcanic glass beads returned by the Apollo missions, announced in 2008, following a careful reanalysis of archived samples using more sensitive analytical techniques than were available in the 1970s, was one of the most unexpected findings of post-Apollo lunar science. This water, present at concentrations of tens to hundreds of parts per million in the glass beads, appears to have been incorporated into the volcanic material from the lunar interior, suggesting that the Moon's mantle retains at least traces of water from the time of the Moon's formation. The source of this interior water has been debated, with possibilities including water delivered by comets and carbonaceous asteroids that struck the early Moon before it lost its initial volatile inventory, water inherited directly from the materials from which the Moon formed, or some combination of these sources. The discovery that the Moon's interior is not completely dry, as was once believed, has broader implications for the giant impact hypothesis of lunar formation, which in some formulations would predict essentially complete devolatilization of the moon-forming material and the absence of any primordial water in the lunar interior. Reconciling the giant impact model with the evidence for some interior water in the moon is an active area of research that is driving refinements to the physical models of the impact itself and the subsequent evolution of the moon. Moon-forming disk, the moon at night, during the lunar day when the sun has set below the local horizon on any given part of the surface, is illuminated only by the soft glow of earthshine, the direct light of visible stars, and the very faint glow of the zodiacal light caused by sunlight reflecting off dust in the inner solar system. In the complete absence of an atmosphere, these faint light sources are visible without any of the scattering that would reduce their visibility on Earth, and the zodiacal light and the faint airglow that are familiar but sometimes difficult to observe from Earth's surface would appear in their full brilliance against the absolutely black lunar sky. The temperature of the lunar surface plunges rapidly after sunset, falling by more than 200 degrees Celsius within the first hour or two, as the thin layer of warmed dust radiates its stored heat into the vacuum. By the middle of the lunar night, the surface temperature has settled to around -170 degrees Celsius over most of the surface, cold enough that any water molecule on the surface would be frozen solid. In the permanently dark polar craters, where the sun never shines, the temperature is even colder, dropping to levels where not only water but carbon dioxide, and even some other common molecules, would freeze out of any vapor phase they might exist in. The long lunar night, lasting about 2 Earth weeks at equatorial latitudes, represents one of the primary engineering challenges for any equipment or habitation placed on the lunar surface, since 2 weeks without solar power is sufficient to drain batteries and allow temperatures to fall to levels that damage electronics and other components designed for terrestrial operating environments. The moon has served as a testing ground for astronomical instrumentation from the earliest days of the space age. Several of the experiments placed on the moon by the Apollo astronauts were seismometers, designed to detect moonquakes and meteorite impacts, and use the resulting seismic waves to probe the moon's internal structure. The seismic network operated by these instruments, which functioned for several years after the astronauts returned home, produced the most comprehensive seismic dataset available for any body other than Earth, and has remained the primary source of information about the moon's deep interior structure for decades. In more recent years, proposals for new and more capable lunar seismic networks have been developed, motivated by the realization that the Apollo network was limited in several ways, including the small number of stations, their restriction to the near-side hemisphere, and the relatively short duration of operation. A new generation of seismometers for the moon has been designed with the lessons of the Apollo network in mind, capable of achieving much higher sensitivity, broader frequency range, and longer operational lifetime than the original instruments. Laser-ranging retroreflectors, another category of scientific experiment left on the moon by the Apollo missions, have been in continuous use since 1969 and remain some of the most productive scientific instruments ever deployed beyond Earth. Several additional retroreflectors have been placed on the moon by the Soviet lunar missions and more recently by the Chinese Chang'e 3 mission, expanding the network of measurement points and improving the coverage and sensitivity of the lunar ranging dataset. The continuing operation of this retroreflector network across more than half a century represents one of the longest-running and most productive experiments in the history of science. The formation of the giant impact basins on the moon required impacting bodies of extraordinary size, large enough that even by the scales of the early solar system, which was far more densely populated with large objects than the current solar system, such impactors were rare. The formation of the South Pole Aitken Basin, the largest impact structure on the Moon, with a diameter of about 2,500 kilometers, required an impactor, perhaps 200 to 300 kilometers in diameter, traveling at a velocity of several kilometers per second. The energy released in such an impact is almost inconceivable in everyday terms, equivalent to billions of nuclear weapons detonating simultaneously. The aftermath of such an impact would have spread melted and vaporized rock across a hemisphere of the Moon and would have sent enormous quantities of material into space, some of which would have rained back down on the Moon over thousands of years, while some escaped to eventually fall on other bodies in the inner solar system. The deep structure of the South Pole Aitken Basin, which excavated material from the upper mantle and spread it across the far side surface, provides an opportunity to study the composition of the lunar interior at depths that would otherwise be inaccessible. A proposed mission, the South Pole Aitken Basin Sample Return Mission, would specifically target this basin and bring back samples from the basin floor, with the goal of determining the comet. The Moon rises about 50 minutes later than it did the night before, a consequence of its orbital motion of about 13 degrees per day relative to the background stars. This nightly delay means that the Moon is visible at different times of night on different nights of the lunar month, with the full moon rising near sunset and setting near sunrise. The first quarter moon high in the sky at sunset and setting near midnight, the last quarter moon rising near midnight and high in the sky at sunrise, and the new moon invisible because it is up during the day and below the horizon at night. The rising and setting points of the Moon on the horizon also vary systematically over the lunar month and over the longer nodal period of 18.5 years. At the times when the Moon's orbital inclination is at its maximum, the Moon's rising and setting points swing to extremes that are farther north and south than the extreme rising and setting points of the Sun, a phenomenon called the major lunar standstill. At these times, the full moon near the winter solstice reaches extremely high in the sky at latitudes where it would normally not be expected to, and it also rises and sets farther to the north and south than usual. Ancient monument builders appear to have recognized and incorporated knowledge of the major lunar standstill into their constructions, with several prehistoric monuments in Britain and elsewhere aligned to mark the rising or setting of the Moon at these extreme positions that occur only once every 18.5 years. The Moon's surface contains iron in the form of both oxidized iron in minerals like ilmenite and in the form of tiny metallic iron grains dispersed through the regolith. This metallic iron was produced partly by solar wind bombardment, which can reduce iron from oxide minerals over billions of years, and partly by the incorporation of meteoritic iron from the countless impacting bodies that have contributed material to the lunar surface over geological time. The total amount of metallic iron in the lunar regolith is difficult to estimate precisely, but it represents a potentially significant resource for future industrial operations on the Moon, particularly for manufacturing structural materials and for producing iron-based alloys from locally available materials without needing to import iron from Earth. The extraction of iron from the lunar regolith would require energy for heating and chemical processing, but the energy could potentially be supplied by solar panels or by small nuclear reactors of the type being developed for space applications, and the resulting iron could be used to manufacture structural components for lunar habitats, equipment housings, and potentially even spacecraft parts for launching from the Moon to other destinations in space. The dream of establishing a self-sustaining human presence on the Moon, one that gradually reduces its dependence on supply lines from Earth, and grows in capability by using locally available materials and energy, has been a recurring theme in proposals for lunar settlement since the early days of the space age, and the gradually accumulating understanding of the Moon's surface composition and physical properties is progressively making this vision more concrete and more realistically achievable. The impact of the Apollo program on Earth's scientific and technological capabilities extended well beyond the lunar science that was its primary scientific objective. The technological challenges computers and the subsequent revolution in computing that the integrated circuit enabled can be traced in part to the demands that the Apollo program placed on the electronics industry. The development of fuel cell power systems for the Apollo spacecraft contributed to the subsequent development of fuel cell technology for terrestrial applications. The development of advanced spacesuit technology for the moon landings required innovations in materials, science, and manufacturing that found applications in medical equipment, protective clothing, and other non-space-related products. The organizational and management innovations developed to coordinate the work of hundreds of thousands of people across thousands of companies on the Apollo program are studied in business schools as examples of large-scale project management and systems engineering. The Apollo program is thus properly understood not as a scientific mission in the traditional sense, but as a vast technological and organizational undertaking whose ripple effects through the entire technological and scientific landscape of the following decades were far-reaching and difficult to fully enumerate, making the moon landing one of the most consequential engineering achievements in human history, not only for what it accomplished directly, but for what it made possible in its wake. The moon presents to observers on Earth a face that has been studied, mapped, named, and incorporated into mythology, calendrical systems, and scientific investigation for as long as human beings have been capable of systematic observation. The patterns of light and dark that form the man in the moon and the various other anthropomorphic, animal, and cultural figures that different traditions have found in the lunar disk are created by the distribution of ancient highlands and younger volcanic plains across the near-side hemisphere, a distribution that has remained essentially unchanged for billions of years, and that will remain essentially unchanged for billions of years more. The features visible to the naked eye, the subtle variations in brightness and color that the unaided human eye can detect across the lunar disk, were the basis of millennia of careful observation before the invention of the telescope expanded the range of detectable detail by orders of magnitude. The telescope revealed the craters, mountains, and valleys that the naked eye cannot resolve, and 2 centuries of telescopic observation, followed by the era of spacecraft exploration, has progressively revealed the moon in ever finer detail, from the kilometer-scale features visible in early telescopes to the sub-meter detail visible in the best current orbital imagery. The moon that reveals itself to successive generations of increasingly capable instruments is always richer and more complex than the moon known to the previous generation. A testament to the depth of detail preserved in this ancient world that has been the constant companion of life on Earth since before the first complex organisms appeared in the seas of the Archean. The water ice at the moon's poles, if it exists in quantities large enough to be practically extractable, represents one of the most important potential resources for future space exploration. Water is essential for human life, necessary for drinking, cooking, and hygiene. Water can be split by electrolysis into hydrogen and oxygen, providing rocket propellant and breathable air. Water can be used as radiation shielding, since its high hydrogen content makes it effective at stopping the energetic protons and neutrons that constitute the primary radiation hazard for astronauts outside the protection of Earth's magnetic field. The potential quantity of water at the lunar poles is very uncertain, with estimates ranging from a few 100 million tons in the most accessible deposits to potentially billions of tons in total across all the permanently shadowed craters. The lower estimates would be sufficient to supply a small lunar research station for many years if the ice could be efficiently extracted. The higher estimates would be enough to support a much more ambitious program of lunar development and potentially to export propellant to fuel spacecraft throughout the inner solar system. The uncertainty in the total water inventory arises from the limitations of the orbital sensing techniques that have so far been used to probe the polar ice, which can detect the presence of hydrogen-bearing material at and near the surface, but cannot accurately determine the depth, concentration, or physical form of the ice at depth. Direct surface exploration of the permanently shadowed craters, using landers and rovers designed to operate in these extreme environments, will be necessary to make the inventory estimates much more precise. And several missions targeting the lunar South Pole are in advanced planning or development as part of the Artemis and International Lunar Exploration programs. The evolution of the Earth-Moon system, from its violent beginning in the giant impact event to the relatively quiescent state it occupies today, has been a story of progressive settling into an equilibrium that is slowly but steadily continuing to evolve. The Moon was born in chaos and fire, a new world assembling itself from a ring of debris in Earth's orbit, while both the newly enlarged Earth and the forming Moon were still largely molten. Over the first few million years, the Moon's surface cooled from its initial magma ocean state, and the outlines of the geological features that would eventually characterize the mature Moon began to take shape. The early Moon was much closer to Earth than it is today, and the tidal forces between the two bodies were correspondingly much stronger, keeping Earth's rotation fast and the tidal heating of both bodies significant. As the Moon receded under the influence of tidal friction, these effects gradually diminished, and the pace of change in the Earth-Moon system gradually slowed. Today, the system is in a state of gradual, almost imperceptibly slow evolution toward a configuration in which both Earth's rotation and the Moon's orbit will have changed so much from their current states that the sky above Earth would look dramatically different to any observer there. The Moon will appear smaller in the sky, the nights will be darker, and the day will be longer, but the Moon will still be there, a constant presence in Earth's sky as it has been for 4.5 billion years, a companion to whatever life may occupy Earth in that remote future, as it has been a companion to all the life that has evolved and lived and passed on Earth since the first simple organisms began their long evolutionary journey in the shallow seas of the early Archean. The study of the Moon has revealed surprising connections between the Moon and many aspects of Earth's geological and biological history that were not recognized until relatively recently. The stabilization of Earth's axial tilt by the Moon's gravitational influence has already been discussed, but the Moon's role in Earth's tidal history is equally profound and less widely appreciated. The early Earth, with a much closer Moon and correspondingly stronger tidal forces, had dramatically more powerful tides than the modern ocean experiences. In the early Archean, when the Moon may have been only a few Earth radii away, and Earth's day may have been only a few hours long, the tides in the early ocean may have been hundreds of meters high, sloshing back and forth across the shallow continental shelves of the early Earth on timescales of hours. The mechanical energy dissipated by these enormous ancient tides may have been an important heat source for the early Earth, contributing to the warmth needed to maintain liquid water despite the fainter early Sunday. The mixing of the early ocean by tidal action, spreading nutrients and organic molecules that might otherwise remain concentrated in isolated pools or vents, may have played a role in the prebiotic chemistry that preceded the origin of life. The rhythmic tidal environment of the early Earth's shorelines, alternately submerged and exposed on timescales of hours by the rapid tidal cycles of the close early moon, has even been proposed as a potential driver of the chemical reactions that led to the first self-replicating molecules, the chemical seeds from which all subsequent life on Earth descended. The moon's role in Earth's history thus extends all the way back to the origin of life itself, making it a participant in the story of biology as well as geology on the planet. It has accompanied for 4.5 billion years. The language of the moon permeates the English language and nearly every other language on Earth in ways that most speakers never consciously notice. The word month is derived directly from the word moon, reflecting the ancient recognition that the lunar cycle provided the most natural unit of time, intermediate between the day and the year. The word menstrual comes from the Latin word for month, which derives from the word for moon, reflecting the ancient observation that the human menstrual cycle has a period approximately equal to the lunar month. The word lunatic, as already mentioned, comes from the Latin word for moon. The word Monday is derived from the Old English word meaning moon's day, a translation of the Latin dies lunae, that was itself a translation of the Babylonian tradition of naming days after celestial bodies. The word crescent, used to describe the thin sliver of the moon visible shortly after new moon, comes from the Latin word crescere, meaning to grow, reflecting the observation that this phase marks the beginning of the moon's growing phase. The word menopause, in some etymological traditions, connects to the moon through its association with the end of the monthly cycle. The words monthly, Monday, month, and many related words in European languages all trace their ancestry back to the same Proto-Indo-European root, meaning to measure, reflecting the ancient and universal role of the moon as the primary instrument of time measurement for human civilization across many thousands of years of linguistic evolution. The moon's linguistic legacy thus runs deep in human culture, an invisible presence in the very words people use every day to talk about time, health, mental states, and the rhythm of life. The surfaces of the lunar mountains, which rise to heights of several thousand meters above the surrounding terrain, are as utterly without life as the maria and the craters and every other part of the moon's surface. Yet they are geologically interesting objects that preserve a record of the processes that shaped the moon's crust over billions of years. The mountains bordering the major impact basins, such as the Apennine Range that borders the Imbrium Basin and rises to peaks of about 5 kilometers above the surrounding mare surface, are composed of ancient highland anorthosite and represent slabs of the original lunar crust that were uplifted and tilted by the tremendous violence of the Imbrium impact event. These mountains are thus survivors of a catastrophe, ancient crustal material that was thrown upward and to the side by the impact that excavated the Imbrium Basin, and that came to rest in its current elevated position as the disturbed terrain settled into a new configuration in the aftermath of the impact. The central peaks that arise from the floors of many moderate-sized craters represent a different kind of mountain formation, driven not by crustal tilting but by the elastic rebound of the crater floor after the initial excavation phase of the impact, a process that causes the deeply shocked and compressed material at the center of the crater to spring back upward, forming a central mountain or peak ring that is characteristic of craters above a certain size. The heights of central peaks in craters of different sizes follow systematic relationships that reflect the physical properties of the impacted material and the mechanics of the rebound process, providing quantitative constraints on the properties of the lunar crust and mantle at depth that can be inferred from measurements of the central peak heights in a large statistical sample of craters. The study of the Moon has benefited enormously from the analysis of samples returned to Earth. Not only the 382 kilograms brought back by the Apollo missions, and the approximately 300 grams returned by the Soviet lunar missions, but also the more recent Chinese sample return, and the large collection of lunar meteorites found on Earth's surface. Laboratory analysis of these samples has enabled measurements of extraordinary precision that would be impossible to make with instruments on the lunar surface or from orbit, including the determination of radiogenic isotope ratios that give age determinations precise to within a few million years for rocks 4 billion years old, the measurement of stable isotope ratios in lunar minerals that constrain the conditions under which they formed, and the identification of trace organic compounds and volatile materials present in concentrations too low to detect with current remote sensing capabilities. The archival study of Apollo samples has been particularly productive in recent decades, as new analytical techniques have been applied to existing samples from the collection maintained at NASA's Johnson Space Center in Houston. One of the most significant findings of recent years, the detection of water in volcanic glass beads within the Apollo collection, was made with secondary ion mass spectrometry instruments that were not available during the original analysis of the samples in the 1970s, demonstrating the value of maintaining a carefully curated sample collection available for reanalysis with improved techniques as they become available. The long-term scientific value of curated sample collections has been confirmed by the Apollo experience, and this lesson has influenced the design of subsequent sample return missions, including the Japanese Hayabusa missions to asteroids and the Chinese Chang'e 5 lunar sample return, all of which have allocated significant portions of the returned samples for long-term preservation against future analysis with techniques not yet developed. The Moon's visibility from different locations on Earth varies systematically with latitude and with the season. At the equator, the Moon rises and sets nearly vertically throughout the year, spending roughly equal amounts of time above and below the horizon. At higher latitudes, the Moon's path across the sky tilts increasingly toward the south in the northern hemisphere, and the Moon's maximum altitude above the horizon depends strongly on which point in the lunar cycle is being considered. The full moon near the winter solstice rides high in the sky at middle latitudes in the northern hemisphere, because the full moon is on the opposite side of Earth from the Sun, and the Sun in December is low in the sky, so the moon must be high. Conversely, the full moon near the summer solstice is low in the sky at northern latitudes. At very high latitudes near the poles, the moon can remain continuously above the horizon for extended periods when it is near the part of its orbit that keeps it above the polar horizon, and it can remain below the horizon for extended periods when it is on the other side of its orbit. This variability in the moon's behavior with latitude was recognized and tracked by many ancient cultures, and the careful documentation of where the moon rises and sets on the horizon at different times of year was an important component of the astronomical knowledge of cultures from ancient Babylon and Greece to the indigenous peoples of the Moon, Americas, and the Pacific. The alignment of Stonehenge and other prehistoric monuments, with significant positions of the Moon's rising and setting points, has been extensively analyzed, and while the specific purposes of these alignments are debated, the level of astronomical sophistication they imply in their builders is impressive and suggests a tradition of careful lunar observation extending back many thousands of years before the invention of writing. The Moon's effect on Earth's ocean diversity and distribution of life in the intertidal zone. The tidal zone, the band of coastline that is alternately covered and uncovered by the sea as the tides rise and fall, is one of the most challenging and most biologically diverse environments on Earth. hosting organisms that have evolved remarkable adaptations for surviving the rhythmic alternation between aquatic and aerial conditions that the tidal cycle imposes. The width and extent of the intertidal zone depends on the tidal range, which in turn depends on the specific local geography, the strength of the tidal forcing from the Moon and Sun, and the resonant properties of the local ocean basin. In some regions with favorable geography, such as the Bay of Fundy in Nova Scotia, where the shape of the bay creates a resonance with the tidal forcing that amplifies the tidal range dramatically, the tidal range can reach more than 15 meters, creating an intertidal zone of extraordinary extent. In other regions with unfavorable geography, such as the Mediterranean Sea, which has only a small tidal range due to the limited connection between this semi-enclosed sea and the open Atlantic, the intertidal zone is very narrow. The biological communities of the intertidal zone are organized into characteristic vertical zones defined by the frequency and duration of tidal submersion and aerial exposure, with different species adapted to the specific conditions of different tidal heights. The study of these communities and their response to variations in tidal forcing has contributed to the understanding of how physical environmental factors control the structure of biological communities, with the Moon's gravitational influence providing the driving force behind one of the most clearly defined and most extensively studied examples of environmentally structured species zonation in the natural world. The composition of the Moon's interior has been inferred from multiple independent lines of evidence, including the lunar seismic data, the gravity field measurements from orbiting spacecraft, the composition of volcanic rocks from the deepest sources within the lunar mantle, and the bulk density of the Moon as determined from its orbital dynamics. The picture that has emerged from these diverse datasets is of a Moon with a relatively simple layered structure compared to the complexity of Earth's interior. At the center is a small metallic core, mostly iron with some sulfur or other light elements, with a radius of perhaps 200 to 300 kilometers for the inner solid portion and 300 to 400 kilometers, including the outer liquid layer. This core represents only about 1 to 2% of the Moon's total mass, far less than Earth's core, which constitutes about 32% of Earth's total mass. Surrounding the core is the mantle, a thick shell of silicate rock that makes up the bulk of the Moon's interior, and that is divided into a lower mantle that shows evidence of being at least partially molten or of having elevated temperatures near the core mantle boundary, and an upper mantle that is generally solid but retains some plasticity at depth. The crust is the outermost solid layer, ranging from about 30 kilometers thick on the near side to 80 kilometers or more on the far side. One of the outstanding puzzles of lunar interior science is the unexplained asymmetry between the near side and far side crustal thickness, which various theoretical models have tried to explain through differences in the thermal conditions prevailing during the cooling of the lunar magma ocean, but which has not yet been fully and convincingly accounted for within a single, consistent model of lunar formation and evolution. The Moon is unusually large relative to the planet it orbits. The ratio of the Moon's mass to Earth's mass is about 1 to 80, making the Moon by far the largest natural satellite relative to its parent planet of any body in the inner solar system. This unusual size ratio has sometimes prompted astronomers to describe the Earth-Moon system as a double planet rather than a planet and its moon, though this designation is not officially recognized, and the conventional usage of calling the Moon a moon rather than a second planet is nearly universal. The next most massive moons relative to their parent planets in the solar system are Titan relative to Saturn and Triton relative to Neptune, neither of which comes close to the Moon-Earth mass ratio. The outer solar system does contain one example of a roughly similar double body situation. The dwarf planet Pluto and its large moon Charon have a mass ratio of about 1:8, making Charon proportionally even larger relative to Pluto than the Moon is relative to Earth. And the Pluto-Charon system is sometimes described as a genuine double dwarf planet. The formation of such large moons relative to their parent bodies appears to require specific conditions that are not commonly met in the solar system, involving giant impacts at the right velocity and angle to produce a disk of debris containing enough material to coalesce into a large companion body. The giant impact hypothesis for the Moon's formation is supported by the unusual size of the Moon relative to Earth, since this hypothesis naturally produces a large companion from the abundant debris of the impact, while alternative formation scenarios have difficulty explaining how such a large moon could have formed in any other way. The long-term future of lunar science is likely to be shaped by a combination of continuing robotic exploration, the establishment of permanent or semi-permanent human presence at the lunar South Pole by hundreds of millions of years, the cause of the near-side-far-side asymmetry in crustal thickness and volcanic activity, the nature and extent of currently active geological processes such as outgassing and tectonic adjustment, and the detailed inventory of the polar volatile deposits, including their total quantity, distribution, chemical composition, and isotopic character. Addressing these questions will require a combination of more detailed orbital mapping, surface exploration, including drilling to sample the regolith at depth, geophysical measurements, including improved seismic networks and heat flow measurements at multiple locations, and the return of additional samples from carefully chosen locations, representing geological units that have not been sampled by previous missions. The Moon's proximity to Earth and the relatively low cost of operations there, compared to missions to Mars or the outer solar system, make it an attractive target for an ambitious scientific program, and the renewed international interest in the Moon in the early 21st century has created the political and institutional conditions for such a program to be initiated and sustained over the coming decades. The reflectivity of the Moon, and how its surface appears in photographs taken from various angles and illumination conditions, reveals much about the physical properties of the regolith that covers it. One of the most striking optical properties of the lunar surface is the opposition surge. Mechanisms contribute to the opposition surge: coherent backscattering, a wave optical effect in which light multiply, scattered within the upper layers of the regolith, is preferentially returned in the direction of the light source due to constructive interference and shadow hiding. A geometric effect in which the shadows cast by surface particles are hidden from an observer in the exact backscattering direction because the particles block their own shadows. The relative importance of these two mechanisms in the lunar opposition surge has been studied through careful photometric measurements at different phase angles and wavelengths, and the results have provided insights into the physical properties of the lunar regolith, including the size distribution of its particles and the way they are arranged relative to each other on the surface. The opposition surge is a general feature of the surfaces of airless bodies throughout the solar system, and the Moon's proximity and detailed study have made it the primary reference standard for understanding this phenomenon in other solar system contexts. The Moon's journey through the cosmos as a companion of Earth extends not only backward in time to its violent birth 4.5 billion years ago, but forward in time to futures that dwarf the entire history of life on Earth in their timescale. The gradual recession of the Moon from Earth will continue for billions of years, the Moon growing more distant by a few centimeters each year until some distant epoch when the process reaches its eventual conclusion. The Sun's eventual transition to its red giant phase several billion years in the future, will dramatically alter the inner solar system in ways that will transform the Earth-Moon system beyond recognition. Whether the Moon survives the Sun's expansion as a distinct body, whether it remains in orbit around whatever Earth becomes in the aftermath of solar expansion, or whether it is eventually stripped away or consumed, is uncertain and depends on details of the Sun's late evolution that are not precisely predictable. What is certain is that the Moon, as humans know it today, this grey world of craters and maria and dust and silence, will persist essentially unchanged for hundreds of millions of years into the future. Its ancient highlands standing as patient sentinels, watching over an Earth that will change beyond recognition over that timescale, while the Moon changes only imperceptibly. The footprints left by 12 astronauts in the fine grey dust of the lunar maria will remain there, perfectly preserved in their original form, for millions of years. A human mark left on another world, at the moment when a single species, on a single planet, first reached out beyond its home and touched another world. That moment, and those footprints, and the Moon that holds them, are among the most enduring facts about the solar system in which Earth and all its life are embedded. And the study of the Moon in all its aspects is ultimately the study of where humanity came from and where it might one day go. The Moon, in its fullness, rising in the east as the sun sets in the west, has served as a backdrop for human experience in every era of human existence. Ancient hunters paused to watch it rise above the savannah. Ancient farmers used its light to work fields after the day's heat had passed. Ancient sailors navigated by its reflected glow across dark seas. Ancient lovers met by its silver illumination. Ancient astronomers tracked its motion across the years and decades and centuries, slowly building the mathematical models that would eventually allow eclipses to be predicted, calendars to be designed, and the mechanics of the heavens to be understood. Children have pointed at its face and asked what it was and why it shone. Poets have searched for language adequate to its beauty and come away enriched but incomplete. Scientists have built instruments ever more powerful to probe its nature and have spent careers studying the rocks brought back from its surface and the data returned by instruments in its orbit, and each generation has found more to discover than the last. The Moon is the nearest other world, the first step outward from Earth in any direction, the most familiar and yet the most alien of all the objects in the sky. It has been everything to different people at different times: a god, a goddess, a clock, a lantern, a laboratory, a destination. It remains all of these things in the contemporary world, and as humanity stands at the threshold of returning to its surface for the first time in more than 50 years, the Moon awaits with the same patient silence it has maintained for 4.5 billion years, holding its ancient secrets in the grey dust of its plains and the ancient grey rock of its highlands, ready to share more of its story with those who come to listen. The quiet that the Moon offers is a different quality of quiet from anything available on Earth. On Earth, silence is always partial, always interrupted by wind or insects or distant traffic or the sound of breathing, heartbeat, the creak of a building settling. The Moon offers a silence that is genuinely absolute, a silence that is the silence of vacuum itself, of space, of the absence of any medium through which sound could travel. The rocks of the lunar surface have sat in that silence for billions of years, unmoved by wind, unstirred by water, unperturbed by the biological activity that churns the soils of Earth in perpetual chemical transformation. The surface the Apollo astronauts walked on had not been disturbed since the last meteorite impact created the small craters visible in their landing area, perhaps millions of years earlier. The dust that clung to their boots had been ground to its present fineness by the patient accumulation of billions of years of micrometeorite impacts. each tiny collision releasing a small pulse of energy that fractured grains into finer grains, ground sharp edges into surfaces still sharper but smaller, and slowly, over geological time, turned the ancient rocks of the highlands and the volcanic basalts of the Maria into the grey powder that covers the entire moon to some depth. In that powder lies the record of everything that has touched the moon since it formed, the chemistry of the solar wind, the traces of cometary visitors, the isotopic signatures of long-ago radioactive decay, the mechanical and thermal effects of countless impacts large and small. The moon as a whole is an archive, the most complete geological archive available in the inner solar system, and its patient silence is the silence of the record room, where 4.5 billion years of solar system history are stored in the grey dust and ancient grey rock of another world. The experience of sleeping under a full moon, its light strong enough to cast shadows and illuminate the landscape with a soft silver glow, is one of the most ancient and most universal human experiences, shared across every continent and every era of human history. The full moon's light has served as a natural illuminator for nocturnal activity throughout human history, extending the effective hours of visibility and allowing movement, work, and social activity that would otherwise be impossible in the darkness of a moonless night. Many cultures have specific traditions and activities associated with the full moon, from harvest festivals timed to take advantage of the extra illumination for gathering crops in the fields, to religious ceremonies timed to coincide with the bright nights of the full moon period, to the simple practice of gathering outdoors to watch the moon rise above the horizon and share in its beauty. The gradual disappearance of dark skies from most of the inhabited world due to artificial light pollution has diminished the practical importance of the moon as a source of nighttime illumination, but it has not diminished the aesthetic and emotional impact of the full moon on human beings who take the time to observe it. The moon rising over the horizon, enormous and orange-tinted as it floats above the distant landscape before climbing into the deep sky and turning to silver-white, remains one of the most accessible and most profoundly moving of all natural spectacles, a connection to the deep past of human experience and to the vast scale of the universe beyond the comfortable familiarity of the earthbound world. The moon rising tonight is the same moon that rose above every landscape in every era of human history, casting the same silver light on a world that continues to gaze upward and wonder. The moon's surface at the microscopic scale is a world of extraordinary complexity, with individual grains of regolith showing evidence of the complete range of space weathering processes that have operated on the lunar surface over billions of years. Under the scanning electron microscope, each grain of lunar soil is seen to be a complex object, often rounded and pitted by micrometeorite impacts, coated with thin, glassy layers produced by the brief but intense heating of impacts, and dusted with nanometer-scale metallic iron particles produced by solar wind, reduction of the iron in the mineral's structure. The glass coatings on individual grains, called patinas, it form when the brief flash of impact melts the outermost surface of the grain and then quenches it so rapidly that the molten material solidifies as glass rather than recrystallizing into minerals. These glass coatings can be analyzed by electron microprobe techniques to determine the composition of the material that produced them, potentially including contributions from the impacting micrometeorites themselves, as well as from the host grain, providing microscale information about the sources of material added to the lunar regolith from extralunar sources. The agglutinates present in the lunar soil, glassy particles consisting of multiple soil grains fused together by the heat of micrometeorite impacts, are particularly informative indicators of the degree of space weathering experienced by a sample since their abundance increases with the time a soil has been exposed at the surface. Younger, less processed soils have fewer agglutinates. Older, more processed soils have more. This relationship allows the maturity of a lunar soil to be estimated from simple measurements of agglutinate content, providing a relative measure of surface exposure age that complements the absolute age determinations available from more complex radiometric analyses. The scientific instruments carried by the Apollo astronauts to the lunar surface, and the results obtained from those instruments both during the missions and from the long-term operation of experiments left on the surface, constitute one of the most valuable scientific datasets ever collected from another world. The portable magnetometers carried by the astronauts on their excursions across the lunar surface allowed the mapping of local magnetic field strength variations on the surface, revealing the existence of localized magnetic anomalies that later turned out to be associated with the lunar swirls visible from orbit. The gravimeters deployed on the surface allowed measurements of local gravitational field variations that provided information about the density distribution of the shallow subsurface, complementing the global gravity field measurements made from orbit by subsequent missions. The solar wind collection experiments. Simple aluminum foil sheets deployed on the surface to collect solar wind particles and then returned to Earth for laboratory analysis, provided direct samples of the solar wind composition that could be compared with the solar wind signatures already detected in the lunar regolith. The cosmic ray detectors left on the surface monitored the intensity and composition of cosmic radiation reaching the lunar surface, providing data relevant to understanding the radiation environment that any future human inhabitants of the Moon would need to cope with. The ranging experiments using laser retroreflectors have already been discussed at length, but deserve mention here as among the most enduring scientific returns of the Apollo program, still providing new scientific results decades after the last astronaut left the Moon. The totality of the scientific instrumentation deployed by the Apollo program and the results it has produced represent an extraordinary scientific achievement, one whose full value has only increased as the data have been studied, reanalyzed, and compared with results from subsequent missions using techniques and knowledge unavailable at the time the original observations were made. The geology of the Moon's polar regions differs from the geology of lower latitude regions in ways that go beyond the simple presence of polar ice in the permanently shadowed craters. The reduced tidal flexing of the crust in the polar regions compared to equatorial regions, the different thermal history of the polar crust, and the unique illumination conditions all contribute to producing a geological environment distinct from the rest of the Moon. The crater populations in the polar regions are statistically similar to those in other highland areas of comparable age, but the morphologies of individual craters can differ in ways that reflect the different thermal and mechanical conditions. The interiors of the largest polar craters, which have been cold enough to preserve ice for billions of years, may also have preserved unusual chemical and mineralogical records of the ancient solar system's bombardment by volatile rich bodies in ways that will be revealed only when landers and rovers explore these environments directly for the first time. The elevated terrain immediately surrounding some polar craters, the crater rims that provide the nearly continuous solar illumination that makes them attractive for solar power generation, offers interesting geological features of its own, including the ancient highland anorthosite, from which the crater rim terrain is composed, and the network of small scarps and fractures that record the tectonic history of the polar crust over billions of years. The combination of abundant solar power on the crater rims, water ice, and other volatiles in the crater floors, and ancient geological records preserved in the crater walls makes the polar regions of the Moon arguably the most scientifically and practically important regions on the entire lunar surface for future human exploration and potential settlement, and the current intense scientific and programmatic attention to these regions reflects a growing recognition of their unique value. The Moon has been visited by spacecraft from an increasing number of countries in recent years, reflecting the broader expansion of spacefaring capability beyond the original club of two that competed in the space race of the 1960s. In addition to the United States, Russia, China, and India, whose missions to the Moon have been mentioned in preceding sections, Japan has sent 2 missions to the Moon. The Kaguya orbiter of 2007 and 2009, which produced detailed topographic and compositional maps of the lunar surface, and the SLIM lander of 2023 and 2024, which achieved Japan's first soft landing on the Moon. The European Space Agency has contributed instruments to several lunar missions, including the SMART 1 orbiter of 2003 to 2006, which was Europe's first spacecraft to orbit the Moon, and which tested the solar electric propulsion technology that has since become an important tool for deep space missions. Israel's SpaceIL organization attempted a soft landing on the Moon in 2019 with its Bereshit spacecraft, which came close to achieving a successful landing but crashed due to a technical malfunction, demonstrating both the advancing capability of smaller non-governmental spacefaring entities and the continuing difficulties in spacecraft. The total solar irradiance received at the lunar surface, in locations that have continuous or nearly continuous solar illumination, is about 1,360 watts per square meter, the same value as Earth's solar constant, because the Moon is at nearly the same distance from the Sun as Earth. This is a substantial power density that could in principle be harnessed by solar panels to provide electricity for lunar habitats, scientific instruments, and industrial operations. The advantage of solar power on the Moon compared to Earth lies partly in the absence of atmosphere, which means that solar panels on the Moon receive the full intensity of sunlight without any atmospheric absorption or scattering, and partly in the fact that certain near-polar locations receive nearly continuous sunlight with very brief interruptions, avoiding the problem of the long 14-day lunar night that makes solar power impractical at equatorial latitudes without very large batteries or other energy storage systems. The engineering challenge of providing power through the 2-week lunar night at equatorial latitudes is one of the primary drivers of interest in near-polar landing sites for human missions. At high-latitude sites with access to near-permanent solar illumination, a modest solar array could provide kilowatts of continuous power for a small outpost, enough to run life support systems, scientific instruments, and basic manufacturing operations such as oxygen extraction from the regolith. Scaling up to larger industrial operations would require proportionally larger power systems, and various approaches to providing tens or hundreds of kilowatts of power at a lunar base have been studied, including large solar arrays, small nuclear fission reactors, and in the longer term, potentially large solar reflector systems that concentrate sunlight onto smaller conversion systems. The Moon, as seen through even a modest telescope, reveals a landscape of breathtaking detail and variety that rewards patient and systematic observation. The transition zone between the illuminated and dark portions of the Moon, called the terminator, is the most revealing region to observe telescopically, because it is there that the low angle of sunlight throws surface features into sharp relief, allowing mountains, crater walls, and subtle ridges to cast long dramatic shadows that reveal their height and topographic character in a way that is invisible when the sun is shining more directly on them. The experienced telescopic observer learns to follow the terminator across the Moon as it advances with the passing of the lunar days and nights, seeing different features in their most dramatic aspect as the solar illumination angle reaches the specific geometry that best reveals each particular feature. The crater Clavius, one of the largest craters on the Moon's near side at about 230 kilometers in diameter, presents a spectacular view in a small telescope when near the terminator, its ancient floor marked by a beautiful chain of smaller secondary craters that give it a distinctive character immediately recognizable to experienced observers. The Great Straight Wall, or Rupp's Rector, a fault scarp about 110 kilometers long in the Mare Nubium, appears as a sharp dark line near the terminator when the sun shines from the east, and as a bright line when the sun shines from the Moon's color, which appears to the naked eye as a shade of gray or silver or cream depending on its phase and the observer's lighting conditions, is in fact slightly more varied than it appears at first observation. Color differences between different regions of the Moon's surface, arising from differences in the mineralogical composition of the Mare basalts and highland anorthosites, can be detected by careful naked eye observation and become clearly visible in color photographs taken with sensitive modern cameras. The Mare basalts of different composition exhibit different shades of gray and gray-blue, with the iron and titanium-rich basalts appearing darker and slightly bluer, and the lower iron and lower titanium basalts appearing somewhat lighter and browner. The highland anorthosite appears lighter and warmer in tone than the Mare basalts due to its high content of calcium plagioclase feldspar, which reflects light more efficiently and with a slightly warmer spectral character. The contrast between the light highlands and the dark Maria is the primary source of the patterns that human observers have perceived as faces, animals, and other figures in the Moon's disk. Color observations of the Moon from orbit by sensitive multispectral cameras have produced vivid false color images that emphasize the compositional differences between different surface units, revealing the Moon as a far more colorful world than its monochrome appearance in casual observation suggests. These color differences are geologically informative, since different rock compositions reflect light differently at different wavelengths, and mapping the subtle color variations across the Moon's surface provides compositional information that complements and extends the more detailed but geographically limited compositional data available from the returned samples. The craters of the Moon, as they appear in photographs taken from orbiting spacecraft, sometimes display features that record aspects of the original impact event with surprising fidelity even after billions of years of subsequent modification. Central peaks, terraced inner walls, and elaborate ejector structures all preserve information about the dynamics of the impact that formed the crater. In the largest craters and basins, the central peaks are replaced by central peak rings, or inner rings, reflecting the different scaling behavior of the crater collapse process at larger sizes. Some craters display unusual morphologies that have been attributed to the presence of volatiles, particularly water or carbon dioxide ice, within the target material at the time of impact. When ice-bearing material is excavated by an impact, the rapid heating and vaporization of the volatile material can alter the shape and structure of the resulting crater in distinctive ways, leaving morphological signatures that can be identified from orbital imagery, and that may help map the historical distribution of water and other volatiles within the lunar crust. The floors of some large craters show evidence of subsequent volcanic activity that has partially or completely flooded the original crater with basaltic lava, creating flat-floored craters with a complex geological history that records both the initial impact and the subsequent endogenous geological processes that modified it. The relationship between crater morphology and the geological context of the target material is a productive area of research that continues to be refined as higher resolution imagery and topographic data become available from successive generations of lunar orbiting spacecraft. The Moon has served as a laboratory for testing ideas about the formation of the inner solar system that would be impossible to test using Earth materials, because Earth's geological record of the first billion years has been almost entirely erased. The ancient highland rocks of the Moon, some of which have ages approaching 4.5 billion years, preserve chemical and isotopic signatures of processes that occurred in the solar nebula before the planets had finished forming, and in the earliest stages of planetary formation, when conditions in the inner solar system were very different from those prevailing today. The isotopic compositions of various elements in lunar rocks have been used to constrain the timing of the Moon forming giant impact relative to the formation of the solar system as a whole, to trace the contributions of different types of primordial material to the composition of Earth's mantle and the Moon, and to study the processes of differentiation that distributed different elements between the core, mantle, and crust of both Earth and the Moon during the first few 100 million years of their history. The hafnium-tungsten system, in which radioactive hafnium decays to tungsten with a half-life of about 9 million years, is particularly sensitive to the timing of core formation in planetary bodies, and has been applied to lunar samples to constrain when the Moon's core formed relative to its overall accretion. The precise value obtained from this system in lunar rocks is consistent with the Moon forming very early in solar system history, within the first few tens of millions of years, supporting the idea that the giant impact occurred during the main phase of planet formation rather than as a late stochastic event. These isotopic constraints from lunar samples thus provide a window into the earliest chapter of solar system history that is irreplaceable and that continues to motivate the collection and careful analysis of both existing and future lunar materials. The sleep-inducing quality of the Moon, its gentle silver light softening the darkness of night, and its rhythmic cycle providing a natural tempo for the passage of time, has been recognized and celebrated in human culture since before written records begin. The Moon rising full and bright above the horizon signals not an ending but a continuity, the same face returning night after night in its endless cycle, the same patterns of dark and light that ancient astronomers mapped and modern observers still recognize after centuries of familiarity. The Moon over the ocean, reflecting its silver path across the water toward the observer, is one of the most peaceful and most universally recognized images of natural beauty available on Earth. The Moon over a sleeping city, the Moon over a forest at midnight, the Moon over the snow, the Moon behind the clouds with a luminous halo marking its presence even when its disk is hidden, all represent familiar and comforting aspects of the natural world that human beings have lived with and found reassurance in throughout the species' entire history. The constancy of the Moon, its unchanging face, its reliable return, its patient presence night after night across all the years of a human life, provides a kind of anchor in the passage of time that gives the Moon a psychological importance beyond its physical effects on tides and light. It is there when you are a child looking up in wonder. It is there when you are old and looking back. The same Moon, the same grey plains and ancient craters, the same silver light falling on a world that has changed in every other respect, while the Moon has remained the same. The Moon is the oldest companion of human beings, the oldest witness to human history, and in its endless round through the sky above us, it carries the story of everything that has ever happened on the world beneath it. In the 4.5 billion years since it first rose over a young Earth and began its long, patient vigil in the sky, the spectrum of light reflected from the Moon's surface carries chemical fingerprints of the minerals present, and the analysis of this reflected light from Earth-based and orbital telescopes has produced global compositional maps of the lunar surface with a level of detail that would have been unimaginable only a few decades ago. Spectrometers sensitive to wavelengths from the ultraviolet through the visible and near-infrared and into the thermal infrared have each contributed different types of compositional information, since different minerals have their characteristic absorption features at different wavelengths. Iron in pyroxene minerals, abundant in the mare basalts, absorbs light at specific wavelengths near 1 and 2 micrometers that are clearly visible in spectroscopic observations of the Maria. The calcium-rich plagioclase feldspar of the Highlander northocite has its own distinctive spectral signature that allows its distribution to be mapped from orbit. Olivine, present in some lunar rocks and in the ejecta of craters deep enough to excavate mantle material, has yet another spectral signature that marks its surface outcrops. The mapping of these mineral absorption features across the Moon's surface from orbit, particularly by the Moon Mineralogy Mapper instrument, carried aboard India's Chandrayaan-1 spacecraft, and by similar instruments on subsequent missions, has produced a global picture of the Moon's mineralogical variation, with a spatial resolution of tens of meters in some cases, transforming the ability to understand the Moon's surface geology without requiring physical sample collection at every location of interest. The integration of these spectroscopic datasets with the topographic information from laser altimeters, the gravity field data from missions like Grail, and the compositional constraints from the returned samples provides a multi-dimensional picture of the Moon's surface and interior that is richer and more powerful than any single type of observation could produce alone. The experience of looking at the full moon through a pair of binoculars for the first time is often described as one of the most memorable experiences available to beginning skywatchers, because the jump in visible detail from the naked eye view to even a modest optical aid is so dramatic. Through binoculars, the craters that were invisible to the naked eye suddenly resolve into dozens of distinct circular features of varying sizes. The mountains along the edge of the Imbrium Basin stand out as a range of bright peaks against the dark mare surface, and the great rays emanating from the crater Tycho become visible as bright streaks crossing the face of the full moon. More powerful binoculars or a small telescope reveal still more, bringing hundreds of craters into view, allowing the terraced walls and central peaks of larger craters to be distinguished, and resolving the subtle color differences between mare regions of different composition that give the Moon's surface a range of tones rather than the uniform gray of the casual glance. The gratification of seeing another world in detail for the first time through optical instruments is a fundamental experience in the history of astronomy, replicated in the personal history of many professional astronomers who recall the moment when they first put their eye to a telescope or binoculars and saw the Moon as a three-dimensional landscape rather than a flat disk in the progen. The Moon is the ideal first target for a new telescope owner or a beginning astronomy student, not only because it is always easy to find, but because the detail it reveals at every level of magnification keeps rewarding increased observational effort, and because the features visible today are the same features that Galileo drew in his sketches 4 centuries ago, connecting the present-day observer to the long history of human curiosity about the nature of the world beyond Earth. The Moon's path across the sky during any given month follows a course that takes it through all 12 of the traditional zodiacal constellations in succession, spending roughly 2.5 days in each before moving on to the next. This path follows closely the ecliptic, the plane of Earth's orbit projected onto the celestial sphere, because the Moon's orbit is inclined only about 5 degrees to the ecliptic. The variation of the Moon's path in the sky with the season means that at different times of year, the Moon follows a high arc across the sky, or a low one. depending on which part of the zodiac the moon is occupying and how that part of the zodiac is oriented relative to the horizon at the observer's latitude. The moon's passage in front of specific stars, and occasionally in front of planets, called occultations, has been used by astronomers since ancient times to study the structure of the sky and, more recently, to probe the moon's own properties. When the moon occults a star, the star disappears behind the lunar limb with a sharpness that is limited by the wave nature of light, and the precise timing of this disappearance can be used to measure the exact position of the lunar limb at that point with extraordinary precision. These occultation timings have been used to refine knowledge of the moon's shape, to map small-scale topographic features on the lunar limb that are otherwise invisible, and in historical records to help refine the lunar ephemeris and test theories of the moon's motion. The study of the moon as it moves through the sky, interacting with the background of stars and other objects in predictable ways, thus connects the practical tradition of astronomical observation to the deep mathematical tradition of celestial mechanics that has been one of the foundations of physical science for more than 3 centuries. The moon, after all that has been said and all that could still be said, remains most fundamentally a world, a place, a physical reality that exists independently of all the meanings human beings have assigned to it across the centuries. Its craters were there before there were human beings to name them. Its mountains rose and fell in the deep time before any eye existed to see them. Its grey plains of ancient lava cooled and solidified in a darkness that preceded not just humanity but the existence of any sentient being anywhere on Earth. The geological record frozen into the lunar surface is a record that the moon made for itself long before it became a record for humans to read. Shaped by forces of gravity and impact and internal heat that operated according to physical laws that were the same then as they are now and will be the same forever. And yet the moon is also ours, in the sense that it is the nearest other world to the world we inhabit, the world whose face we know by heart, whose cycle structures our months, whose light has illuminated our nights since before our species existed. The relationship between Earth and Moon is one of the oldest and most consequential relationships in the history of the solar system, a pairing that has shaped both worlds through their mutual gravitational embrace and that has given Earth the tidal forces and the axial stability that may have been important ingredients in the development of the complex life that eventually produced beings capable of wondering about the moon's nature and sending explorers to its surface. The moon rising tonight over the horizon carries all of this history in its ancient grey face, and the silver light it reflects toward Earth is the same sunlight that has bathed this pair of worlds through 4.5 billion years of their shared journey around the Sunday. The deep geological time recorded in the rocks of the moon's surface is a concept that requires some contemplation to fully appreciate. The oldest rocks on Earth that can be reliably dated are about 4 billion years old, found in remote regions of Canada and Greenland, where the ancient basement has been exposed by erosion. On the moon, rocks of comparable age are found across much of the highland surface, and some samples from the Apollo missions have been dated to 4.4 to 4.5 billion years, ages that approach the age of the solar system itself. A rock sitting on the lunar surface near the Apollo landing sites today may have been lying in essentially the same position, at most moved slightly by the disturbance of nearby micrometeorite impacts, for 3 billion years or more, slowly accumulating the isotopic signatures of cosmic ray exposure and the chemical signatures of solar wind implantation that allow its surface exposure age to be measured by sensitive laboratory techniques. The stillness of the moon is a geological stillness that has no analogy on Earth, where rocks are erosion and biological activity. On the moon, nothing churns. The rocks that formed 4 billion years ago, when the highland crust crystallized from the cooling magma ocean, are still there, lying essentially where they came to rest after the last major disturbance moved them, waiting with geological patience for whatever comes next. This stillness makes the Moon the most faithful recorder of the early history of the inner solar system, available for direct study, and the scientific value of this record is one of the most compelling arguments for continued exploration and eventual permanent human presence on the Moon that might allow its geological library to be read in its entirety rather than sampled from just 6 locations over the brief span of 3 years that the Apollo program represents. The Moon at its setting, as it descends toward the western horizon in the hours before dawn, displays the same gentle face as always, but takes on the warmth of sunrise before it sinks below the horizon, its color shifting from the white-silver of the high night sky toward the orange and gold that the long path through the atmosphere imparts to any celestial body near the horizon. This last view of the Moon before the morning light grows too bright to see it, the final setting of the Moon above the horizon as the sky lightens toward sunrise, has a quality of peaceful completion that many observers describe as among the most beautiful of all the Moon's manifestations. The Moon has been there all night, traveling its arc across the sky from its rise in the east through its highest point to this final descent in the west, casting its light on the sleeping world below, and now it gives way to the sun whose light will dominate the day. The same cycle will repeat tomorrow night, and the night after that, and the night after that, into an indefinite future that extends far beyond the span of any human life, and far beyond the span of the human civilization that has watched and measured and wondered at the Moon for so many thousands of years. The Moon will still be there when the last star visible from Earth's surface in the 21st century has set and risen again through hundreds of generations of human watchers. Its ancient craters and volcanic plains will still carry the record of the solar system's violent youth preserved in the grey dust that blankets their surfaces, patient and unhurried, waiting to be read by whatever future generations of curious minds find their way to its surface, with their instruments and their questions and their enduring human need to understand the world around them. The Moon is the great constant of Earth's sky, and its study is the oldest and most universal of all the sciences that human beings have pursued in their long effort to understand the universe in which they find themselves. The study of the Moon encompasses physics, chemistry, geology, astronomy, history, mythology, engineering, and the full range of the human sciences and humanities that have engaged with the Moon as both a physical object and a cultural phenomenon. The physicists have calculated its orbital mechanics and the tidal forces it exerts. The chemists have analyzed the compositions of its rocks and soils. The geologists have mapped its surface and reconstructed its 4 billion-year history. The astronomers have measured its distance and tracked its motion through the sky with increasing precision across centuries of observation. The historians have documented how its study contributed to the development of mathematics, navigation, and the physical sciences. The mythologists and anthropologists have catalogued the extraordinary diversity of human cultural responses to the Moon across every civilization that has left a record. The engineers have designed the spacecraft and the spacesuits and the life support systems that made it possible for human beings to actually visit the Moon and return safely. And the explorers, the 12 people who actually walked on the surface of another world, have brought back the irreplaceable experience of standing in a place no human being had ever stood before, and looking back at the blue world, hanging in the black sky, and knowing that everything that had ever happened to any human being had happened on that single beautiful sphere suspended in the void. The Moon is all of this, a physical object and a human story, a scientific puzzle and a cultural touchstone, a destination and a mirror in which humanity has seen its own curiosity, courage, and aspiration reflected back across the centuries. The study of the moon is ultimately the study of what it means to wonder at the universe and to pursue that wonder wherever it leads, even if it leads, as it did for 12 extraordinary human beings half a century ago, all the way to the surface of another world. The gravitational constant, the fundamental physical constant that governs the attractive force between masses and that appears in Newton's law of universal gravitation, was first accurately measured using terrestrial laboratory experiments in the late 18th century. But the moon provided the first clear demonstration of its universal validity. When Newton showed that the same gravitational acceleration that causes an apple to fall to the ground in an English orchard also keeps the moon in its orbit around Earth, he demonstrated for the first time that the physical laws operating on Earth's surface are the same physical laws that govern the motions of celestial bodies millions of kilometers away. This unification of terrestrial and celestial physics was perhaps the most revolutionary intellectual achievement of the scientific revolution, and it was made possible by the existence of the moon as a nearby celestial body whose option underlying all of modern science. Every subsequent application of Newtonian mechanics to the motion of planets, moons, asteroids, and spacecraft, and every subsequent development of Einstein's general relativity that extended Newton's theory to the strongest gravitational fields and the largest scales, builds on the foundation of that original demonstration provided by the moon's obedient circulation around Earth, according to the mathematical rules that Newton derived from the study of falling apples and orbiting moons together in a single unified theory of gravity. The astronauts who walked on the moon universally described the experience as profoundly transformative, an experience that reshaped their sense of who they were and what mattered in ways that no other experience they had had could match. The scale of the universe as experienced from the lunar surface, the vast black sky above, filled with stars in a clarity and abundance, never visible from Earth's atmosphere-blurred vantage point. The absolute silence in which their voices existed only within the closed environment of their helmets and spacesuits, and the sight of Earth as a distant blue world, one planet among billions in an incomprehensibly large cosmos, all contributed to a philosophical reorientation that several of the astronauts have described as one of the most significant experiences of their lives. Edgar Mitchell, who walked on the moon looking back at Earth from the vicinity of the moon. Al Worden, who orbited the moon alone in the command module during Apollo 15, while his crewmates walked on the surface below, described the experience of being on the far side of the moon, completely cut off from any radio contact with Earth for 45 minutes at a time, as the most alone a human being had ever been in the history of the species, 3,500 kilometers from the nearest other human beings in any direction. These personal testimonies from the people who have actually made the journey to the moon add a dimension of human experience to the scientific and historical facts that no amount of description from Earth can fully capture, and they remind us that at its deepest level, the exploration of the moon is not just a scientific or technological enterprise, but a profoundly human one. 3 hours of moon facts to fall asleep to ends here, but the moon itself continues its eternal circuit through Earth's sky, the same ancient face returning night after night as it has for 4.5 billion years. Its craters remember impacts that occurred before life existed on Earth. Its volcanic plains preserve lava flows that cooled when the most complex organisms on Earth were single-celled. Its polar ice has been frozen since before the first fish learned to breathe air. Its regolith has been accumulating the chemical signatures of the solar wind since before the first dinosaur walked the Earth. And somewhere on its surface, in the grey dust of the Sea of Tranquility and the Ocean of Storms and the Taurus Littrow Valley, the 12 most distant footprints in human history wait in perfect preservation for whatever future brings. The Moon is patient. It has been patient for 4.5 billion years. It will be patient for billions more. And every night, when it rises above the horizon and fills the sky with its silver light, it offers to anyone who pauses to look up at it the same gift it has always offered: the quiet reminder that the universe is vast and ancient and beautiful, and that we live on a small blue world accompanied through the cosmos by a grey companion world that has been part of our story from the very beginning. Sleep well under the light of the Moon.